Please take your seats comfortably. Our volunteers will facilitate the seating arrangements and ensure everything runs smoothly. As we prepare to begin, I would like to remind you that today's symposium promises to be an enriching experience with insightful presentations and engaging discussions. Let's get comfortable and let the knowledge sharing commence. Before we begin, please ensure your mobile phones are in silent mode. We also have designated break area for networking and refreshments. If you need assistance or have any questions, please don't hesitate to reach out to our friendly volunteers who are in and around us. So thank you for your cooperation, and let's make this a memorable event. So it's our great pleasure to invite Dr. Shastry sir, founder and chair, sage and professor from Bradley University, USA, onto the stage to deliver the welcome address. So Dr. Shastry sir is a renowned expert in microwave field and has been instrumental in organizing this symposium. So his dedication and passion for the field are truly inspiring, and we are honored to have him lead us today. Please join me in welcoming Dr. Shastry sir onto the stage.
Good morning. Good morning, everyone. Dear distinguished guests, esteemed colleagues, honorable delegates, and friends. It's my honor and privilege to welcome you to the inauguration of Shastry Associates Global Enterprises, in short, SAGE, and the first SAGE International Symposium in Advances in Wireless Technologies. We will hear more about how this organization came about later on. We have put together today for this event an excellent program for you with distinguished speakers from India and US, both from industry and academia, as well as networking sessions and student industry interactive session for the first time. And that will be very useful to students to learn from what is expected in industry from them. I'm looking forward to a great day with you today, with your active participation in this event. Thank you once again for your participation. Please enjoy the day. Once again, it gives me immense pleasure to welcome you. Now I request Dr. Parimala Prabhakar and Dr. Rosalind to take over and conduct the proceedings. Thank you very much.
Thank you for a very good, warm welcome, sir. So it is my privilege and honor to welcome everyone for the inauguration of the SAGE and the first SAGE International Symposium on Advanced Wireless Technologies. And here is a brief overview of today's program for information. So in the forenoon session, we have the inauguration of Shastry Associates and Global Enterprises, SAGE, by the distinguished guest, Mr. Kiran Kumar, from Space Commission, and the guest of honor, Mr. Sanjay Nayak from Tejas Networks. So this will be followed by the first SAGE International Symposium. So we have experts from industry and academia sharing their valuable experience and knowledge on 5G, 6G communications, RF energy harvesting techniques, supply modulated amplifiers, then interesting art of system on chip with 4 Cs in the sessions to be followed by inauguration. So also we have arranged an interesting student industry interaction session held with the top industry members like Sankhya Lab, Astrom, RFIC, and many more. So this will be followed by an entertaining and mesmerizing cultural event, that is string puppet show by famous entrepreneur. So in between we have coffee breaks, lunch, dinner, and high tea arranged for refreshments and networking. So now I would like to request Immaculate Rosalind to take over with the introduction. Yes.
Good morning, everyone. It is a privilege to invite our respected invocators, Mrs. Maithili Prakash and Mrs. Nalini Melikot, to the stage to invoke the blessings of the Almighty and set the tone for our symposium. For your information, Mrs. Maithili Prakash and Mrs. Nalini Melikote have trained in Carnatic music for a number of years, both retired from banking service a few years ago. As of now, they are more into singing devotional songs, shlokas, and bhajans. We welcome you, ma'am.
Ajum nirvikalpam nirakaravekam Ajum nirvikalpam nirakaravekam Nirananda Ananda Advaita Purnam Param Nirgunam Nirvishesham Nireham Parabrahmarupam Ganesham Bhajema Parabrahmarupam Ganesham Bhajema Parabrahmarupam Ganesham Bhajema Yakundendu tushara haradhavala Ya shubhra vastrannvita Ya veena varadanda manditakara Ya shveta padmasana Ya brahmachyuta shankara prabhutibhihi devyai sada pujita samam patu saraswati bhagavati nishesha jadyapaha Shrungapuradeshwari शृङ्गपुराधीश्वरी शारदे शुभमङ्गले सर्वाभीष्टप्रदे शृङ्गपुराधीश्वरी शारदे 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 शङ्कर सन्नुत श्रीपद्मचरण शङ्कर सन्नुत श्रीपद्मचरण सकलकला विशारदे वरदे सलहिलताये समगान प्रिय शृङ्गपुराधीश्वरी शारदे 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 करुणी संवश्रुति गतिಗಳ ಮಾತೆ करुणी संवश्रुति गतिಗಳ ಮಾತೆ कमनीय सप्त स्वर सुशोभित काव्यगान कला स्वरूपिणी काव्यगान कला स्वरूपिणी कामितदायिनी कल्याणी जननी शृङ्गपुराधीश्वरी शारदे शुभमङ्गले सर्वाभीष्टप्रदे शृङ्गपुराधीश्वरी शारदे शारदे शारदे
Thank you, Mrs. Maithili Prakash and Mrs. Nalini, for your beautiful invocation. You have set a wonderful tone for our symposium. As a token of our appreciation, we would like to present you with a small gift. Please accept this as a symbol of our gratitude. We are honored to have you with us today. Now, it is a privilege to request our distinguished guests to take their seats on the stage. Firstly, we request our chief guest, Shri S Kiran Kumar, former Secretary, Department of Space and former Chairman, Space Commission, to please take a seat. Next, we request our guest of honor, Mr. Sanjay Nayak, co-founder and former CEO, Tejas Networks, to please join us on the stage. We also request our executive board members, Dr. Prashad Shastry, professor from Bradley University, Dr. M.H. Corey, former technical director, Alcatel-Lucent Bell Labs, Dr. K.D. Nayak, former director general, DRDO, Ms. Aparna Sankara Subramaniam, senior product manager, Verdant Telemetry and Antenna Systems, Kochi, to take their seats on the stage. Ms. Scarlett Dowd, visiting faculty, Electrical and Computer Engineering, Bradley University, will be joining us online from US. Please join me in welcoming and honoring our esteemed guests and executive board members. I also request the volunteers to greet the dignitaries of the dais. We now proceed to the lamp lighting ceremony, a symbol of igniting knowledge and enlightenment. We request our chief guest, Dr. Kiran Kumar, to light the lamp, followed by our guest of honor, Dr. Sanjay Nayak, and our executive board members.
शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तु ते दीपज्योतिर्नमोऽस्तु ते दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपो हरतु मे पापम् सन्ध्यादीपनमोऽस्तु ते ओ दीपब्रह्मरूपस्त्वं ज्योतिषां प्रभुरव्ययः ओ दीपब्रह्मरूपस्त्वं ज्योतिषां प्रभुरव्ययः
Invoking the divine blessings, may the light of knowledge guide us and illuminate our path through successful and enlightening symposium.
यावत् सूर्योदयो भवेत् रवेरस्तं समारभ्य यावत् सूर्योदयो भवेत् यस्य तिष्ठेत् गृहे दीपः तस्य नास्ति दरिद्रता शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तु ते दीपज्योतिर्नमोऽस्तु ते शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः
We are honored today to have with us the distinguished members of our executive committee. Their leadership and insights are pivotal. Let's welcome the members of the executive board to the stage to share their valuable inputs. I request Dr. Prestige Shastry, as a pioneer, to take over a session.
Thank you, Dr. Rosalie. No, I don't need it. It's fine. So welcome again. So people often ask me, or even if they don't ask me, they have this in their mind as to why this organization was started. What is the reason and how it got started? So I want to address that first. Oh, okay, sure. Green, okay, sure. Thank you. So on periodic visits of mine to India since 2012, particularly 2012, I've been coming even before that, I have been invited to give talks and conduct workshops in educational institutions and R&D labs. With my associate, Dr. M.H. Corey, he's one of our executive board members. I have conducted workshops in RF and microwave systems and wireless communication areas, which were very well received. Okay. From these experiences, I realized that there was a need for imparting knowledge and skills across many spheres, including students and faculty in colleges, as well as engineers in industry. In 2018, we expanded the group beyond Dr. Corey and myself into a group of experts from industry and academia to conduct these workshops upon request. We didn't seek these opportunities. Whenever we were invited, we were ready to conduct these sessions. The group included individuals with decades of experience in top engineering industries, both in India and the United States. Currently, we have over 30 experts in the group in various areas, not just RF and microwave, encompassing wireless communications in general. And it is growing. SAGE is now an international group of highly qualified and accomplished engineers and entrepreneurs. We have amongst us entrepreneurs who have started their companies and running them very well, with a long track record of engineering and technology experience in industry and academia. Their knowledge is very well rooted both in the fundamentals of electronics and communication engineering in general, and in applied electromagnetics, radio frequency and microwave circuits and antennas, and wireless communication systems in particular. At SAGE, our associates disseminate knowledge through courses, tutorials, and workshops to provide deep understanding of the subject matter and insights therein, as well as guidelines for design and applications of the theory. They also impart skills through training. The skills could be software-driven skills, soft tools, use of soft tools, as well as test and measurement equipment. In order to do that, we have to partner with other companies who make them. They also impart skills. They impart using customized courses, tutorials, and workshops on demand. Consulting services are also available upon request to provide engineering solutions. Okay. So, having said this, in 2024, this year, I registered the company as Shastry Associates Global Enterprises, SAGE, as a limited liability company in the United States. We decided to organize a formal inauguration of SAGE in Bangalore, India. Why Bangalore, India? Because that is becoming the hub of the International Symposium on Advances in Wireless Technologies. So with that, I just want to give you an overview of our organization. Yeah? Oh, if you got it. I think we can. Okay, thank you, volunteers. So I just will briefly go over the mission, vision, and the goals of this organization, and later my colleagues in the executive board will explain more from their perspectives. So the mission is to provide knowledge, skills, and solutions in the areas of applied electromagnetics, which will cover a number of subjects which we know, and wireless systems. That's the mission. The vision is to be the leader in providing knowledge, skills, and solutions in RF microwave circuits, antennas, and wireless systems engineering and technologies globally. So that's the vision. So what are the goals of this? The goals are education and training. One of the goals is education and training, which includes providing tutorials on practical engineering and technologies, and on RF, millimeter wave, and microwave circuits, components, subsystems, and systems. We have our website. We have a website, rftutorials.com. And the other goal is to develop tutorials, courses, workshops, and provide them to the college graduates, engineers in industry at appropriate levels, on-site, off-site, online, and via our website, the rfcourses.com. So that's also another goal. And then, of course, as I said, which this is being talked about in the country quite a bit, skills training. I hear this everywhere, everywhere I go, particularly with India going heavily into semiconductor manufacturing. I have been seeing that there is not much emphasis on IC design in the country. There is more, they are talking about manufacture, but we also have to train people in circuit design, chip design, and so on. VLSI there is going on, but not in high frequency areas. So that is skill development. And so we want to provide the RF soft design tool, skills in use of RF soft design tools, and test and measurement equipment. So of course, we have to partner with other companies who make this. So, we are not equipped with these tools at this point in time, and there are companies who manufacture the equipment, manufacture these tools, so we have to partner with them. So that is a very important goal that we want to accomplish. And the third goal, of course, is consulting, to provide engineering consulting services, because we have different experts in different areas, so it's natural for us to offer these services too. So broadly, SAGE Institute for Education, and then SAGE Education and Training, and SAGE Consulting for consulting services. So these are the goals. And this is our current committee, which has an executive board of 5 people. And then we have an advisory board. Dr. Surendra Pal is here. We are happy to have him in the audience today. He has been our great supporter. And Professor Mahadevan is unable to, he's traveling abroad. He's unable to join us. And Professor Raghavan was supposed to attend, but because of some medical reasons, he's unable to, but he has joined us on Zoom. He is there. So they have been guiding us, and and the executive board has been very active. And then we have various other committees I have not listed here. The website committee, social media committee, and so on and so forth. But these are the leadership committee in short. So with that, I will end my talk here, and I request Dr. Corey to come to the stage and talk about SAGE. Thank you.
Good evening, everyone. Welcome to this symposium. Particularly, I'm very happy Mr. Kiran Kumar is here. I still remember I have a photograph of him giving me an award, Distinguished Fellow or something in IEEE or IET. Thank you very much for joining. As Dr. Prasad mentioned, SAGE is planning to do a lot of activities, primarily in the area of wireless and RF. As Dr. Surendrapal is here, he says RF and microwave engineers are a vanishing tribe. It's like tigers, you need to conserve them. So we thought that we will also do some effort from our direction to make sure that the microwave community and the RF community survives and thrives. I think with also help of Dr. Nayak, Dr. Tejas is there, that some effort is also being made, that a center of excellence, probably, hopefully it will come up in the area of RF and wireless at IIIT. Let's see how this develops. So this is an effort that is going on. In this direction, SAGE is trying to do some little contribution, this, and expand into all domains of the areas which associate with RF and microwave and wireless communications and MMIC design and various other aspects of it. Slightly trying to give there are lots of people who are conducting these RF courses. There are many people who do these things. But we are a different type. There is a distinct group which works on this RF and microwaves. They always talk in terms of the amplifiers, oscillators, couplers, and all aspects of this. Our goal, we only focus on certain terminologies like what is the 1 dB compression point, what is the third order intercept point, what is the phase noise, what is the noise figure, what are the harmonics and things like that. We always go deep into it and then we work on that. There is this wireless communication community, this is primarily in the digital and software domain. They primarily look at the coverage, capacity, throughput, quality of service, delay, jitter, packet loss, error rate, bit error rate, block error rate, voice quality, latency, bandwidth, and things like that. Unfortunately, these are two different communities work in silos. They don't interact with them, and then we need to establish this link between that. That is one of the aims of this society or this organization, to make sure that seamlessly, if I say I need a system with certain amount of noise figure or the phase noise and certain other parameters, what is the final effect of that on my bit error rate? And things like that, at a system level, there is no courses which is being offered to make sure that we link up these things, and then some effort we are already doing, me and Dr. Prasad working on certain things. Extensive research part of it, hopefully Dr. Tejas and the Institute's Center of Excellence will do the core research part of it. But here we are trying to see most of it is that educate people. You design a low noise amplifier, you say you with a certain noise figure, and then what is that specification of that? Or you design an MMIC, or you go and buy from mini circuits or anyone else certain components. How do you choose those values? There are 10 different parameters. What does it mean? This is what we started doing some work on that. When Dr. Prasad mentioned about that, we started conducting certain courses initially last 10, 15 years, which we have been doing. He said that he will be conducting on the RF. He is a core RF. He will go nitty-gritties of everything related to the power amplifier, low noise amplifier, distributed amplifier, and everything else. He wanted to do that. There was no way I could match and do some, though I'm also from microwaves, I could teach that one. So I said, I took a safer option and said, I will talk about the systems part of it. So that was easier for me to say, if you put an amplifier, what is your 1 dB compression, or what is the linear zone in which if you're working on a 5G communication systems, and then you would like to work on a 256 QAM, what is the linear zone in which you have to do, and what is the backup that you need? All these things, how do we relate with the design of your power amplifier? Whether you go in for a power amplifier, which is the most expensive part in your BTS system, E-Node system, that if you put that, and then how do you design to make sure that what linearity you do, or you do a pre-distortion, how do you compare between these things, and then do that. So he started teaching about the core microwave systems and subsystem part of it, and then I started looking at the system part, and we started working on that. Of course, to the level of extent that he goes, the first course when we offered, he said, I will not teach unless everyone comes with a Smith chart. It was so difficult for people to make sure that everyone comes with, or we provide a Smith chart to them. Now, of course, electronic Smith charts are available, but first time when he said that I will not teach unless they have a Smith chart, and then I explained the stability circles to them and things like that. So from there we have moved on, and then we have done, but now we are looking at an integrated approach of making sure that all aspects of the system, as Mr. Sanjay Nayak was mentioning, the product is the end goal, and that is which we have to concentrate and make sure that for that we look at the link budget, but even link budget and things like that, everything that we need to look at it, every individual component, whether we design ourselves or we buy from someone else, how do we choose that? And then make sure that what is chosen, that's the design side. It's not rocket science or something new I'm talking about it. But people, when they learn, they need to appreciate and understand. If a digital person in wireless communication, they need to be slightly aware of the nuances associated with the RF part of it, RF front-end part of it, and then how do we make sure that these aspects are brought into, that's what we want to give emphasis in this, and not just routinely conduct a certain amount of courses which is being offered either at the graduation level or at any other organizations give certain courses. So that kind of emphasis is what which we would like to bring. And then fortunately, myself, Prasad, Nayak, we all come from the same place, IIT Bombay. We were trained, Prasad and myself were students of Professor Mahapatra. Dr. Nayak also worked with Professor Mahapatra from IIT Bombay. So for a long time we were thinking in terms of what could be done, and then Dr. Scarlett and Dr. Aparna also joined us, and then we have expanded, and with the blessings of Dr. Surendra Pal and everyone else, we have expanded it into a center or organization or LLC as you call it. With this, we would like to really impart knowledge which is not uniquely taught at every other place, that so that we bring a blended holistic system view going into depth and the width of the things, and then make sure that this all happens. And I'm sure that with the blessings of everyone, we will be able to do. This is just a glimpse of what I just wanted to say, and thank you everyone for coming here. Thank you. I would now request Aparna to come and say a few things.
Okay. So my name is Scarlett Dawood. I'm so excited in industry and also in industry itself for RF and wireless applications and technologies. So there's about 3 areas that I want to talk about. The first area is the transition of newly graduating engineers from a theoretical textbook environment to a hands-on practical work environment. So this also applies to both students that graduate with bachelor's degrees and students who graduate with master's who are in the industry can also reach out to the RF Tutorials website and use this material. And then, of course, the third one is training. Again, Dr. Shastry shared how we can bring in training for skills because there is sometimes a need for skills training, and this will apply to like design software applications and also test equipment. Because typically at universities, not all universities have robust RF programs, and so not all students are exposed to the proper design software applications and the proper test equipment. So I think SAGE is going to be a unique place that can help in this transition. A second area that SAGE can help fill in the gap is for experienced professionals who are already working as RF and wireless engineers in industry that need further education and training, because there's the RF and wireless technologies, they are constantly evolving and advancing. You know, technology every year or 2 years, there's something new in the RF and wireless arena. And so professional engineers in industry, they have to keep abreast on the latest. And so I believe also SAGE will be a good place to fill in the gap through the different courses and tutorials and training. And also professional engineers sometimes need one-off consulting help. And so SAGE will be able to provide consulting support when requested. And the third area that I believe SAGE is going to be pivotal for for the services that we provide is also for experienced professionals, but for those who do not have any RF and wireless background. Some examples are those of different engineering professions, such as software engineers, systems engineers, or support engineers, like test engineers and different technical roles that engineers take on, as well as managers and leaders. Just, you know, being that I've worked with different levels of management, and so some of them, you know, they just understand the word Wi-Fi or Bluetooth, or, you know, they don't understand the details or just even a general overview. And so with, again, as I mentioned, with RF and wireless technologies being implemented into almost all electronic products, automotive applications, and industrial applications, SAGE can fill in the gap for these experienced professionals that need to expand their knowledge so that they're able to understand these technologies and work with their teams. And we can help them with targeted workshops, seminars, and training in addition to the services mentioned earlier. So this is exciting, and I'm so glad to be part of this diverse team of experienced professionals, academic scholars, and creative entrepreneurs at SAGE. So welcome, everybody. I wish I could be there in person, but I will be watching online and be coming in and out at different times. And we are honored to have you with us as we present our first international symposium on advances in wireless technologies. Thank you. Now I would like to, you know, whoever next is going to come, I don't know if it's going to be Aparna or Dr. Nayak.
Good morning to our distinguished guests and participants. I welcome you all to this inaugural function. I'm really honored to stand here at this inaugural function for this remarkable initiative called SAGE, which is established by our esteemed and beloved Professor Dr. Shastry. And today, it not only signifies a chapter for us as individuals, but also for the wireless communication industry in India. So with over a decade of experience in this field, starting my career as an antenna design engineer and growing on to become a senior product manager in the same company, I have witnessed firsthand the exponential advancement of technology and the critical importance of continuous learning. The RF and microwave industry, which is part of the wireless communication, continues to grow and innovate at an incredible pace, creating an increasing demand for skilled professionals who are to be equipped to meet the challenges of not only today, but also for tomorrow. To succeed in their careers, students have to understand how the industry works, what are the demands of the industries, how to manage their time with coming out with quick designs, and also to improve their practical skills like my colleagues spoke about. This is not only a problem for the students themselves, but also for the industries, where we are forced to spend a lot of time and resources in training and upskilling the new hires. So this is very expensive and time-consuming. And this is where an organization like SAGE comes into play. So SAGE is basically designed to create a platform both for aspiring engineers as well as existing professionals. So by offering courses, tutorials, workshops, and the like, we would like to aim to bridge the gap between the academic knowledge and the industrial requirements. And SAGE has about 35 plus people, and it is continuing to grow continuously, who are from varied academic and industrial backgrounds. And they're also from different geographical locations. So they have a lot of experience in their careers and can share the insights from their own careers. So this mentoring aspects is very crucial for especially young professionals who can navigate their career paths more effectively using a mentor. One of the key benefits of SAGE is the opportunity to connect with peers and industry veterans. So networking can open doors, leading opportunities for employment, for collaboration and partnerships. This might not be available otherwise. Our courses, which we are planning to design, will be structured, will bring a structured approach to learning, covering crucial topics, especially in the RF circuits, components, systems, and subsystems. And these will help the participant gain a coherent understanding of the core concepts. In India, where the tech landscape is evolving continuously, the RF and microwave sectors has an immense potential for growth. And SAGE is here to empower the individuals by equipping them with the necessary skills to meet this demand effectively. We are not just creating a learning platform, but we are also fostering a community where we will be focused on innovation, collaboration, and progress. In conclusion, I would like to express my gratitude to Dr. Shastry for envisioning this group and bringing it to life with his unwavering support. And I encourage all of you to actively participate and share your ideas and be part of this thriving community. Together, let's cultivate the next generation of RF and microwave engineers. And it is a pleasure having all of you here today. Thank you for your attention. I would like to call in Dr. Nayak for the speech.
So I'll not take much time. First of all, I would like to thank Professor Prasad and the other sages who invited me for this. And I would like to briefly bring out why SAGE is required and why I am part of this stage. Some of my previous DRDO experience I started my career in way back in as we three myself S and X band phase shifter projects under Professor Mahapatra. And when I moved to the IGMDP program after graduating and then from IIT Bombay, he says we should work on 35 gigahertz and 94 gigahertz. It was a quantum jump for us, basically working on S-band phase shifters. As you remember, I think Dr. Corey, we were working for that PSM-33 radar of Bell, indigenous component for making S-band phase shifter drivers and all those things. And straight away going for 35 gigahertz because in our NAG missile, we had an FF mode, and that was working at 35 gigahertz, the total radar plus figure processing, everything. And I worked in the lab where the whole core group was developed for that. We didn't know anything, basically, because we had worked on S-band, the parameters there, all WR28, including the technology, manufacturing, because we didn't have even the WR28 waveguide manufacturing, CNC machining, then getting the components and designing our own MIC circuits, all the way to the Herculean task. So we learned basically by doing online. I mean, we learned, we didn't have exposure it, but the one thing what I was telling that our generation, I don't know, the younger generation, I hope, takes that spirit. We said we'll do it. We didn't say that, oh, can you do it? Should you get into that? It is too tough. No thinking on that. When Kalam said we should do it, we will do it. Jump. That's all. Jump in a well, you jump into the well. That's the spirit we had. And I am very happy that it's successful now. Basically, our all Helena fire and forget radars, 35 gigahertz, even 94, 35 is used in Trishul, and 94 gigahertz in our NAG missile. It's called Helena now, and production. Because we started working in basics from that. I'm starting from scratch, including technology, machining, everything. I mean, there is nothing that except the components, we had a problem. Basically, we had device problems. And even we started getting them in India. We started making efforts in near IIT Kharagpur, impact diodes making and all things we tried. But somewhere in semiconductors, we are still lagging. But other technologies, I think we have full confidence that we should be able to do it, including designs and manufacturing, integration and all things. We're in good now. You might have heard of BrahMos missiles, everything. All the things are designed and made in India now. There is nothing except a few devices. That also we're trying to make it in now with our semiconductor policy. So that's my background. But because why I'm saying that is, after that, somehow in the 90s, I switched over to the digital side. Somehow I moved from microwave to supercomputing in Anurag, and I was leading semiconductor fabs, 2 fabs we created for, again, I kept my link in semiconductors. In GATEC, we did up to 40 gigahertz semiconductors. We manufacture our space-qualified fab. I think Dr. Kiran Kumar will say that we approved space-qualified fab is there. We established all the things we did. But the problem I found, I'm telling you now, is when we started off, we had a good strength, I'm telling you, not only in DRDO, even academics also. In IIT Kharagpur, there is strong groups, and professional B.N. Das and all there, even IISc, Macha, Pacha was there, IIT Delhi, Professor Bharti Bhatt and all were there. But somehow that group started shrinking, okay. And I heard that this is not only the Indian phenomena, somehow microwave and RF, because maybe later than 90s, when Narayan Murthy's and all these big service providers came, what they did was in the IT field took off. And the microwave somehow went down is because of two reasons, they say. One is in US, I don't know it's true, but it is a heard story, is that US also the microwave engineers were started reducing because after the late 80s when the Cold War, Russians exploded and the Cold War stopped, US defense started reducing the things because the technology was not required. Mostly was earlier, the RF side was in the defense side, radar and things was supported by defense. But that was not there. So then it started reducing there. Here also we had went into the IT field because IT field, they got the more money for the effort. The RF side is the tougher side, they get lesser money. So that's how it happened somehow. And the community of RS started reducing in India. Okay. So, and we have a choke point now. But now, again, it is RF field is getting into things because of 5G, 6G, and all things are coming in. Communication, revolutionary space is coming in. And now we want RF engineers, we are not getting it. So there is a choke point coming in. So when SN, I called it signal to noise Prasad. Okay, our colloquial language. SN called me. So then we said, yes, I agree. But right now I'm not in the field because I myself called is, after my superannuation, myself called as CCIT. I'm a cardless independent thinker. I don't work for anybody. So, but I am working with what I call is not working in IIT. Yes, I'm advisory for a few IITs, but working on IITs is because integration indigenous technologist. Okay, I try to integrate now all technologies in India, different field. I'm 4G, 5G, even data centers, photovoltaic. Now recently I got into agricultural things and all things. When I come to the integrating the people, I feel very happy. At least some products have come. And 4G, 5G, I think you have succeeded. I think thanks to Sanjay and all things, we have got our own now indigenous 4G and 5G system getting into production. Because bringing the professionals and coming together solves the problem. That's how I learned last 5-6 years. That is the major problem. So we have got a lot of technologies. I don't think we have knowledge deficiency, no. And working together, and bringing them together, that is the point. So from that angle, during I think, what used to meet, Woodland Hotel, talks when Prasad used to come during his winter vacations here, we used to talk, myself, Corey and Prasad used to talk, why not somehow help this dwindling generation to flourish, like what Corey said, tigers. Why not support some tigers at least, karke? And I'm happy that some old tigers like Surendra Pal and all have come. I hope we'll proliferate this, tiger generation and RF sites. And I'm very happy that at least few students are coming. Do hope that students pick up this knowledge and flourish. That's our aim. SAGE, that's what we started for. Basically, training and that sort of thing. In that, I found one problem was that as a group, we felt maybe we may be getting about 35, 40, 100 professionals. But the professional knowledge is not only sufficient, but we have to give them practical knowledge. So then I started off the line, then how to get that. For example, one is what is the problem in RF side? One is costly equipment for test equipments are very expensive. Even the design equipment and softwares are very expensive. Even a startup has to come, he may not have to have that much money to put it in. So the idea is that whether you can somewhere you create these assets and the startup community as well as the training, practical training we can give. From that point of view, I started talking to friend Professor Karandikar of DST Secretary and try to CSSI and try to get some center of excellence. And I'm happy that Professor Das is here, whether we can get. So that is the exercise I'm trying to pull in now. So create a center of excellence here in Bangalore where will be equipment and software, everything will be there. Some of the students, I'm just saying we have trained them in the colleges and all things. He has a bright idea, he can do it. But if you want to start startups, investments he will not be able to do. So whether he can use this facility, that is the idea I'm trying to create. I do hope that it succeeds. That is basic initial idea. And we raise a proposal now. I've been talking to Professor Karandikar, DST, and even a DOT secretary, whether we can pull in our resources, and industries and the government can come together, startup excellence, and some academics are there in IIITB, and if they give us the land and some acquisition, we should be able to do. So I do hope the SAGE also and strength and the Center of Excellence can come together and make this field flourish. That is my idea. Okay. So thank you for giving me an opportunity to talk to you. Thank you.
Thank you very much, sir. So we would like to thank all the members of Executive Board of SAGE Committee. So it is completely filled with the knowledgeable tigers in RF and communication. So thank you very much, sir. So there is a verse in Bhagavad Gita, Nahi gnanena sadrisham pavitram iha vidyate tat swayam yoga samsiddha kala atmani vindati. So in this verse, Lord Krishna emphasizes the supreme value of knowledge as a purifier and the path to achieving spiritual realization. So we are filled with such knowledgeable persons. So I thank everyone. So next, let us proceed with the next talk by chief guest. So I would request and also invite Dr. Keshava Dattatreya Nayak, so former Director General, DRDO, and a respectful member of our SAGE community, to introduce our chief guest, Mr. Kiran Kumar, sir. Please welcome, sir.
Good morning once again. So it's my privilege to introduce S Kiran Kumar. So I don't think I'll take much time, even though his biodata is long biodata, I know, because he has a lot of achievements and a lot of things. But Kiran Kumar, everybody knows about it. I don't think I have to introduce Kiran Kumar, right? So whenever I said, whenever we have a problem, what you do? You look up, right? Or a problem is there, or whatever you achieved, you look up. So that means look up means space. So when you say look up, it's Kiran Kumar, okay? So then Kiran Kumar doesn't require introduction. Any problem is there, we look at Kiran Kumar. So just for basics, 2-3 things, I will take it out. So AS Kiran Kumar is the chairman, Physical Research Laboratory. Presently now, he is the chairman of that, Management Council and member, Space Commission of Government of India. As you are aware, Space Commission is the largest body now, which is governing all the space technologies in India. He served as Secretary of Department of Space and Chairman of Indian Space Research Organization during 2015 and 2018. Okay, so, I don't want to take the age and all things, dates, because we were born the same year. Okay, I don't want to tell the date. Okay, he has worked a lot in space technologies. I don't want to go, because that's why when I said, when Prasad asked me whom we should get into the things, suddenly Kiran Kumar's name came to me, because space and RF, I thought one common man who can, drive the things. So that's what I thought. I'll request Professor Kiran, Dr. Kiran Kumar to come out today here. He has steered the implementation of application-oriented Indian space program, which has facilitated rapid development of countries' many important spheres of observation, communication, navigation, meteorology, and everything. And as you are aware, space, as far off, the communication has to be for RF side. There is no other way. There is no connectivity by wired connectivity. So he is a spaceman, and he is for RF man from our angle. So his number of societies, that's what A to Z societies, he is a member, and I call it A to Z. And there are about 15 societies I will not read. About 3-4 only I will read. Shri Kiran Kumar has been president of Aeronautical Society of India. He is fellow of Indian National Canada. Again, under 10 associations are there. He is a, academy and things. And he has been conferred with honors causa of DSC by 18 Indian academic institutions. Okay, that's the important thing I'll put. So excellent work, and he has technically has been very competent. He has been co-authored 85 publications in various national and international scientific journals and conferences. In recognition, again, he has got lot, maybe about, I was counting about 15 to 20 awards. I don't want to count him. So with these achievements, I don't think I have to introduce Dr. Kiran Kumar. I don't want to cut his time, please, Kiran Kumar ji. Thank you, Kiran Kumar. I don't want to cut his time, please, Kiran Kumar ji. Thank you.
Because sages for us are the real sources of, you can say, the information and the entire set of activities that happen on earth. We are reminded of the great 7 sages. So one of the key things, if you look at human being right from maybe the very early part of his own existence on planet Earth, what he has been trying to do is, in many ways, look at his surroundings, look at nature, and try to mimic what he sees there by his own efforts. And through that, he has been evolving. If you look at, for example, in the very early, he can survive. Then he started looking at maybe some sticks, bows and arrow. Like that he went on, and then he found a way of surviving so that he himself can exist for doing things. Then he looked at, while he was walking, there were many animals which were moving much faster than him. So he thought, how can I domesticate them and ride them? Similarly, he saw birds flying. See, today, you know, we have already built planes, rockets, and we are going beyond Earth to other planets, etc. So in this way, when you are looking at what human being is doing all along is trying to look around, make observation, and for doing this observation, obviously, he is provided with 5 senses. And each of these senses have their own bandwidth, their own limitation. As more and more research goes into that, we realize what we are able to see through our eyes is only 400 to 700 nanometers of the electromagnetic radiation. But we see in nature, there are so many other life forms which are making use of different wavelength region. And then, in many ways, human being has already made Atindriya Gnana development by going beyond this 400 to 700 nanometers by building equipment. Like if you take an infrared camera, what is it trying to do? It is trying to capture what is present in nature and bring it into the domain of human visibility by translating it and then either displaying it on a screen or whatever. So bringing it within 400 to 700 nanometers. So in the same way, if you look at microwave, radio waves, and then X-rays, a whole lot of observation capability using electromagnetic radiation, which is beyond the human senses of our immediate capability as provided to us is the eye. Then we have already done a whole lot of development where we are able to see what is happening in nature by building specific tools, technology, capability. And in this, the ability of what we are talking about today, wireless technology, is a huge progress. And in this, I would like to touch upon few of these aspects because on the topic of wireless technology itself, there will be many experts who are going to talk about. But I want to bring to you a different perspective in life and then how, as we are keeping on improving our ability to see what's happening around, how humanity is facing new challenges and how things are moving ahead. So one of the things what I was talking about is we are all endowed with basically 5 senses through which we are taking inputs. And then all the information that comes to us through these sensors is interpreted by a control system which is provided to us. And what all constitutes that control system, I'm sure you will be able to visualize yourself. And then after making sense out of these sensory inputs, the control system also creates instructions for the actuators provided to us for dealing with our world. See, as a young child, we listen to lot of noise happening around us. But then the controller within us tries to mimic that sound. So that's how I will learn Kannada if I'm in Karnataka. Somebody will learn in Germany. All that is happening is controller is trying to mimic the sound it is hearing and reproduce the same sound through the actuators it is provided. That means our vocal cord system or the speaking mechanism which exists is an actuator through which we are interacting with the universe. Similarly, if you look at the child keeps learning from its surroundings, how to get up, how to walk, how to move around. So it's trying to make sense out of all this. All this is also showing us that what is actually perceived by an individual is more dependent on how the controller interprets and makes itself capable of dealing with its surroundings. So many times you would have heard, Pratyakshoto bhi pramanit karo, or Pratyakshavidaru pramanisi nodu. That means what is seen or experienced by your sensors, the information that comes to you through your sensor is actually interpreted by your controller, and you have a perception of what is happening. So this is where psychologists tell us that many times what we interpret is not reality. Actually, same picture is shown to us, one person looks in that picture, very different things from the other person. It is because it is a perception of that controller based on what it has seen, which is making sense and not reality. So today, in many ways, if we look at, I would like to just give you a couple of examples. I'm sure you will be able to appreciate in the context of what you are trying to do in SAGE itself. See, today, if you look at a drama, what is a drama? If I ask you, probably you will say drama is a process where there is a director, there is a story. Director wants to convey something to the audience. He does it through stage and actor. So drama is a process of these 5 elements. Similarly, if you look at a cinema, basically same, except now the experience of the audience is very dynamic, much more vibrant, and the mechanism of creating is different. But here also you have a director, a story, and then director is conveying to the audience through stage and actors. Then I come to our video games. I'm sure all of us have done video game in some way. What's happening in a video game? We are in front of a screen, whether it's a mobile or a TV screen, or we are in front of a screen. We are shown audio and video, and there is a trigger in our hand, either joystick or steering wheel, and then based on the trigger, something in the system takes the data from what it is stored and creates the new audio and video and shows it to us. That means if you look at here, the person who wrote the video program, this particular game, video game, he has created certain algorithms, put it in a processor. There is a data stored in the memory, and as the trigger comes, the processor computes new audio and video and shows it to us on the screen. Now I want to link it to our dreams. What is a dream? If you look at dream, you can say is nothing but even when all the sensory inputs for us are dormant, there is a mechanism within us which is able to show us an audio and video experience. So if you look at this and try to match, you will find that the controller which is taking care of us is probably the director, and it has a mechanism within us where it can trigger the audio and video experience. And obviously, what are the contents? How does it get its content? You are sure that every one of us, based on our life experience from our early days, as we see here, study, we keep on storing the information within us. So if you say there is a memory, and that memory content can be one of the sources for the director to create the content of an audio and video which we experience as dream. And then similarly, if you look at this controller is taking care of all the actuators, does it have any other source of information on the basis of which it can do? Obviously, you will realize that all life forms come at birth, some basic information which is accessible to that controller. And you can say this is a memory which has come from the birth process. Now what gets stored in that? Actually, you can keep going back and seeing that the egg and sperm which join to form a cell, that cell over a period of the entire mammal's womb, under the control of the parent's control system, it is evolving from a single cell into a full-fledged life form. So here also, there is a lot of interaction going between the thought processes and the evolution of the life form. Now I want to come to the point, another important point of wireless communication. See, we talk about our 5 senses as the basic elements through which we are getting inputs. And I'm also telling that you have a control system which has access to 2 types of memory. One memory which you have created based on your own experience, another memory which you have got from your birth process. But are these 2 the only sources of information for your controller, or does it have access to anything else outside? See, if you were to look at universe as a whole, this universe, you minus the universe, for you is the rest of the universe. And through the birth process, what we talked about, what information can come, obviously, is at the time of release of that particular egg or sperm from the parent body, whatever got recorded in that, we all know DNA records a whole lot of information. There is a lot of research which is done, and we are also told that the information stored is much more than all the recordings we have been able to do so far, etc., etc. But then, while information is there in that, what information is there is what is the decoding that is going on, and people are working to do genetic engineering, etc. When you say a whole lot of this is happening. My point to bring it to your awareness is the following. See, if this were all the limit, don't you think the controller has some limit to his access to outside world? What it has learned by its own experience of seeing, reading, and experience is one information, and something which has recorded and come back from the genetic history of that lineage. Outside that lineage, whatever has happened in the universe, there is no information present in that. So if you look at beyond the 5 sensory organs, do we have an ability to do communication, and are there methods of doing it? If you look at, we are all making effectively use of a gadget, and this gadget, if you see mobile, outside the physical boundary of this object, it is able to send information, and what is sent from here can be picked up not only on Earth, outside Earth also now. That means outside the physical boundary of the object, information exchange is happening. So if we are all human beings or also some life forms, and if human being has been trying to mimic nature all along and bring into reality what he has seen or what he is visualizing, and if and I also keep looking at, is there anything that human being has created so far, the concept of which does not exist in nature? I'm sure if you keep trying, and if you find any such thing, I'll be more than happy to know about it. But then, so far as I see it, it is only whatever is present in nature, human being has tried to bring it into reality. Initially, it was physical, reducing his physical labor. You have built machines which can do 10,000 or even more people's job at a time. Intellectual capability through computing system. Today, we have gone beyond digital limits. We are getting into quantum. But in all this still, this is all what is happening in nature. So that means human being can also do atindriya gnana acquisition. Now, in some way, what I said, atindriya gnana can be even what the microwave shows, what X-ray shows, what infrared shows, because it is outside the limits of our sensor. So to that extent, that's also an atindriya. But still, is there a mechanism possible which is outside this? Are we endowed with some mechanisms which, if you work on and then make it active, can you do effective communication? See, suppose in a robot today, when we send it to explore Mars or this, what are our problems? We are trying to find out in these gadgets, build in, based on all our knowledge, features into that, so that not only it performs the actions we design, but also to protect itself from means conditions which are harmful to it. We do not know many things. So if the gadget crashes because the environment it encountered, we lose, we have to rebuild the whole system, take the trouble of sending from Earth to Mars. But then, before it actually perished, if there was a way of getting that information from that gadget, capturing that condition which occurred, and then somehow reach it to us, the next version of the design will be a better version which can deal with that problem. That's how you can say artificial intelligence, AI, machine learning, all becoming a problem which is being solved by human beings. And then such things are being built into the gadgets. So in the same way, if you look at, that means the asli intelligence we have is what is being mimicked in artificial intelligence. And many things what we are building is operating differently from what you see in nature, simply because whatever happens in life form has a limitation in terms of time constants and how much period is there for it to respond. So you see a whole lot of things. You are trying to build chips which can work much faster, starting with huge one. Today we have hit the limits of digital electronics, and earlier analog was being overtaken by digital. Today we are going back to a combination of hybrid analog and digital. Analog which is actually mimicking the way the neural networks operate, etc., etc. So in all this, one basic point I was trying to make is, many of us during our younger days, terrestrial tower was the way by which we were getting signal on the television. If on a particular day our antenna on our rooftop is not pointing correctly to the terrestrial tower, no signal on the TV. So we go align it properly. A proper alignment makes the communication effective, and that decoding everything happens. So same way, is it possible for life forms to look at communication beyond the sensors provided to that life form at birth? And is yoga, which is supposed to be the union between you and the universe, a process by which such communication is possible? And those who put in the efforts of trying to make that mechanism work for them, are they the people whom you call Siddha Purushas or saints, etc., etc.? Anyway, this is just a thought process I want to leave. I want to leave and link it to what you are doing. See, what human being is doing all the time is making observation, and observation through sensors, and those sensors being progressively made finer and finer. See, if you want, he was talking about signal to noise ratio, picking up signal in the background of noise. Any sensor has huge amount of noise, and you want to reduce the noise, you are trying to make it operate at lower and lower temperatures, going down to cryogenic temperatures, etc. So same way, in your own system also, if in the presence of all the noise, the system is not working, you think of doing meditation to suppress all the external noise, and in that safe mind, that state of mind, you are being able to communicate with external things is a possibility. So coming back to today's discussion, my idea of telling you all this is, basically what human being is doing all the time is making use of becoming aware of the self, and also through that process provide better and better opportunities to the life forms around it, appreciating how life can survive. Today, if sustainability on planet Earth is a problem, it's a problem more so because human nature is also, when any new discovery happens, there are people who are looking at how can I make use of this discovery for my economic benefits or my group's benefit or my nation's benefit, etc. It all happens at very different level. So in the process of actually propagating the use of that particular development, many times we overdo things, and you have heard of the case of the golden goose type of thing. So we think we can extract more by killing the goose itself. So we create another set of problems, and that set of problems are being solved by next generation, which becomes more and more intelligent, because the whole process of evolution itself is continuously happening. So in this context, the importance of becoming aware of our own self, and also becoming aware of what human being is doing to other forms of life on planet Earth, and how planet Earth can be left suitable for survival of future life forms, is one of the key aspects. And this is where sages of this land, and this sage also is attempting to bring in awareness to all those who are not aware of the thing. See, when you talk about a particular aspect of a microwave and RF technology, if I have not learned it during the course of my studies, but I am required to know about it, if there is a way of finding out if there is somebody who can help me achieve that, it will serve the purpose. So let me really compliment SAGE for taking up what they are doing and also wish them a great success in their effort. Thank you very much.
Sir, your thought-provoking and inspiring speech has left us all in awe. So your words have ignited a spark within us, and we are grateful for the wisdom and the insights you have shared. As a token of our appreciation for your outstanding address, we request Professor Shastry sir to honor Mr. Kiran Kumar. Please stand. Thank you, sir. Thank you, sir. Yes. With great enthusiasm and anticipation, we welcome Mr. Sanjay Nayak, sir, to deliver the keynote address on opportunities and challenges for India to become a technology product nation. As we look forward to Mr. Nayak's address, let us prepare to engage with his ideas and gain knowledge that will enrich our understanding and drive our progress in this field. So it is our pleasure to invite Dr. M.H. Kori sir, to a renowned expert and a respected member of our SAGE community, to introduce our guest of honor, Mr. Sanjay Nayak.
I'm told I've got 2 minutes. No time. Mr. Sanjay Nayak, it's a great pleasure to introduce him, a privilege. Mr. Sanjay Nayak is the co-founder of Tejas Networks, which is the first Indian deep technology product company that has successfully grown from being a startup to a publicly listed company with a market cap over 20,000 crores. And it's a unicorn, and we are extremely proud of you, sir, and the Tejas, that the remarkable achievement an Indian company can do. We are very, very proud of you. Mr. Nayak, before that, has served as a CEO and MD of, he has served as MD and from the inception from 2000 till his retirement in 2023. Super. Prior to founding Tejas Networks, Mr. Nayak was the managing director of Synopsys India, world's leading electronic design automation company, having worked in both USA and India. He is a highly respected thought leader. I'll skip all those things because I'm running out of time. But his achievements, as Nayak, Dr. Nayak was mentioning about Mr. Kiran Kumar, so many achievements. He is a fellow of Indian National Academy of Engineering, Technology, Sarabhai Award for the Indian Electronic Semiconductor, Hall of Fame, Distinguished Alumni Award from Birla Institute of Technology, Hall of Fame, North Carolina State University. Mr. Nayak did his bachelor's degree from Electronics and Communication from Birla Institute of Technology, Mesra, and where he was the gold medalist. And he did his MS In computer engineering from North Carolina State University, Raleigh, USA, there are so many achievements. I request Mr. Nayak to come and kindly speak.
Thank you. First of all, it's a privilege and honor to be invited for this talk. So I must thank you, Shastry ji, Dr. Nayak and others. And clearly, I mean, talking after what Dr. Kiran Kumar gave is a very difficult task, you know. So when I was thinking of what to talk today, there were two choices in front of me. One, I could talk a little bit about technology, communications, RF, and so on. But I thought I would be inadequate in terms of the kind of expertise that exists here. So I thought I'll skip that part. So the second choice I thought would be something which would be very interesting, because we all, you know, being techies and technologists over the years have, you know, not been able to crack the code as to how come India, with so much of tech firepower and so much of manpower, why can't we have our own product companies? Why don't we have our own Cisco's, own Huawei's, own Apple's, own whatever of the world, or Tesla's, XYZ, and what is wrong and why we can't do it? So I thought, having a little bit of a practitioner's experience doing this for the last 24 years, let me share that insight, and it will solve two problems. One problem it will solve is, of course, hopefully it gives a top-down system-level architecture's view of what do we need to do as a country. And more importantly, it will also solve the problem that Dr. Nayak said, that all the good engineers are running away and doing software. So how do we get them to really do products and do something more exciting in life as well? So that's really what I'll try to do. So really, I think let's start off with the basics in terms of, you know, we're all saying that India needs to become a Viksit Bharat by 2047. So what are the economic imperatives? So we are all saying that we grow 7% GDP and will happen. 7% GDP is not going to happen if we don't have turbochargers in the economy. And in my mind, the turbochargers are products. You know, this is what gives you nonlinear growth. And unless we create those turbochargers now, and we have not done it in the last 50, 60, 70 years, we will not become a product nation. Some headwinds will come and things won't happen. Second very important thing today in India being talked about is jobs. You know, we don't have jobs. What do we do to create jobs? We have so many young people in the country, but they don't have jobs, and it can create all kinds of problems. Unfortunately, if we go after jobs in a wrong way, where either they don't generate enough money, so they're not high-paying or reasonably paying jobs, and secondly, if they're not long-term sustainable. And what I mean by that is, if you go after manufacturing jobs or any job which is low-end, sooner or later going to get eliminated. AI and automation will eliminate a lot of, you know, jobs which are currently in required menial things. Second, there's another aspect of jobs is that the reason some of the low-end jobs will come to India or have come to India is because our cost structure of the economy is low. And we all want our people to become rich. We all want our per capita income to go. So as soon as that happens, those jobs will go to the next geography where things are cheaper. So the garment industry started from US, went to, you know, Singapore or Taiwan or China, then came to Vietnam, then to Indonesia, then to India, now to Bangladesh, to Sri Lanka, Kenya, Timbuktu, wherever. So I think we need jobs which are long-term sustainable, okay? So that is what requires a different kind of thinking. Otherwise, what is called is a middle income traps. If you look at Thailand, if you look at Malaysia, these are all countries with a per capita of $8,000 to $12,000, and they are stuck, you know. The reason they are stuck, Mexico included, is because if you don't build a innovation-led economy, you know, for the long term, you become more expensive from $8,000 to $10,000. Your country will become uncompetitive for lots of jobs. So I think that's the thing which we need to understand. And I think we have been talking about manufacturing coming in the country, but unfortunately, we are really assembling a lot in the country. We are not really manufacturing. And assembly doesn't give you the value add, doesn't give you the economic thing. So there are a lot of policies, and I'll not name, where the incentives that the government is giving is higher than the value addition which is being done in the country. So as a net result, if you're producing $100 billion or something, India is giving $2 billion to someone else abroad to, you know, do this, and we're not even creating jobs here. So I think this is a serious problem that needs to get solved. There's another aspect which we are not considering today, but it will be very important, is the strategic imperatives. See, having a secured and trusted infrastructure is critical. Telecom, digital, cybersecurity, energy grids. If we don't secure them, we cannot be a developed nation. Anybody can come and poke things in our economy, and within seconds, and I'm not talking minutes, we will be at the mercy of someone else. We just saw what happened a month back when a glitch in the computer, a minor glitch in the computer, basically created havoc. Just imagine if someone, and we are all technologists, it takes few seconds to log into any system, everything is connected, you can shut down the whole network, you don't need any traps, backdoors, nothing. You just need a remote login into a communication network, and within seconds the country can be put to a dead stop, right? So I think it's very important that we have control, we have technology. Second aspect, today, India is the darling of the world. Everybody wants to sell their goods to India, because of economic considerations. As recent as 2000, we were all subjected to technology denial, right? So what happens is suddenly we become so dependent on everybody else, we don't create anything else that, whosoever decides, okay, I'm not going to give you this chip, I won't give you this computer, I won't give you this raw material, and we are stuck as an economy. Can we be a developed economy without having such kind of things? The third aspect is the resilient supply chain. And in fact, there's a very interesting book I was reading, A Material World. It traces back to 6 minerals which basically pretty much control everything in the world. And unless we come up with a game plan of having some control on those minerals, which in turn will become the building blocks of the supply chain, we will be again dependent on someone else. And these are all problems which we have to solve today, because these problems take 5, 10, 20 years to solve. And we're not thinking hard enough in the country to do this, And the last part is the new age economy. I mean, if you really see the way the world is happening, a lot of new technology, new industries are coming. Are we going to be participating them as a front runner, or are we going to participate them as a backbencher? Will you only be consumers of all of this? And if you have to do this, we have to build that depth in our technology ecosystem, our economy, and so on and so forth, without which we can't get there. And the glaring thing in front of us is you're already a top 5 economy. The number 1, number 2, number 3, number 4, they're all innovation-driven economies. They're not manufacturing, they're not services, they're not things which are counting on natural resources. So it's a wake-up call that if you want to be moving from number 5 to number 3 or number 2, we better start doing something about this as a country. And really, we have to start thinking of becoming an innovation-driven, product-driven nation, right? Sorry. Then the next thing is, so what are the challenges, Why we are not there? So first of all, one more thing we have to understand this is like the Olympics, being a product nation is like an Olympics. And unfortunately, in a 100-meter race, we're already starting 50 meters behind. So we have to, first of all, catch up all the lost time for whatever reasons. And I'll go into actually one slide in terms of what are the reasons as well, because unless you don't understand what the problem was, how do you come up with the new solutions? I think we've got to catch up things very fast. We are running out of time. And we've been great consumers, right? We consume technology very quickly, but we have not been creating. Whereas what China did very smartly in the last 25 years, while the Chinese market consumed all technologies, in parallel, they started to create technologies. And they used a set of processes, means, copy, beg, borrow, steal, do whatever, but they made it a clear focus that we got to be creating technologies as well. Whereas in India, we were very happy with consuming technology. So for example, the blatant mistake I think we did as a country was, because we wanted to promote the IT services industry, we made all the computers and hardware and everything zero duty. But as a result, the entire hardware industry got killed in one shot. The price for which we are still paying. That was the ITA one which we signed in 1997, for example. So I'm just giving you that example that things have to happen. The mindset is still missing in the both the private sector as well as the government, because we are very happy with this services thing. The first was IT services. The newer thing is the GCCs, the Global Capability Centers. We're very happy. Apple sets up 1,000 people seats here. Cisco has 2,000 people. We're very happy with that. All these cushy multinational jobs have come. We're not hungry enough to say that that's just one part of the whole ecosystem, right? Investment in R&D is ridiculously low, 0.6% of our current GDP, whereas all our global peers are 2.6, 3.5 of a GDP which is 4 times, 10 times bigger than us. So on an absolute basis, we are 1/10, 1/50th of amount of money we are investing in R&D compared to what the world is, what other 4 people whom we compete against are doing. I'm not talking about general, right? So this is how far behind we are in the race. The third part I want to talk about, and very interesting insight I learned. We all talk about the demographic dividend. So we have the youngest population in the world. It's a great asset, absolutely. Now, our average age in India is 29 years today, somewhere about that. It's been proven, a lot of research has been done over the last 50, 60 years, that as soon as the average age of a country crosses 40 years, economy starts slowing down, okay? So we just got about 11 years left in that sense to get our act right. Because if we miss this opportunity, you'll have a very large population, very little economic value add, no way of feeding all of that, no way of creating sustainable jobs, and all the other things which I mentioned in the previous slide. So I think there's a need to really wake up and do something very different. And if this wasn't enough, AI is going to be a disruptive factor in terms of the economy, the job, and so on and so forth. I don't need to get down to that, right? Now, so if this is the situation, what do we do? So we got to jumpstart. So we have to have a very different mindset. This is not the time where we start from first principles and build everything from ground up, because we'll miss the bus. I mean, it's not going to happen. So we really need to figure out, how do I create a product ecosystem by getting all the background technologies? And what I mean by background technology, if you really see all the products, all the tech that gets consumed in the world, I put it under 2 buckets, Let's call it a established or mature products, which is 98% of the world's products in tech. And 2% are the only ones which are disruptive products coming for the first time. The 98% of the product in the world, there's always some companies already having something available today. You want to go buy a car, there's a Tesla EV, for example, there's a Tesla, there are zillions of things. So you're not the first guy producing that car, right? You want to buy a telecom equipment, there are 10 companies. Everything, there's a lot of incumbents. So there's a whole bunch of history of background subsystems, technologies, patents, IPR, et cetera, which goes in, right? So if we start today, unless you get access to all of that stuff, you cannot jumpstart. You need to load yourself with all of that. And we've not been thinking in that direction, right? So we have to work on a war footing to use M&As. For example, Chinese went ahead and copied stuff from there, from the world. Maybe we can't do that, but why can't India Inc. or India as a government go and buy lots of tech companies around the world and quickly jumpstart? It'll give you 2 benefits. One, it gives you all the background IPR technology, and it gives you the market access into those countries. And to give you an example, in 2007-8, when the Lehman Brothers crisis happened, the financial crisis, the auto industries in Europe and US really went through a tailspin. So most of the companies, went south, and the auto ancillary industry in Europe particularly got hurt badly. So many Indian auto ancillary companies went ahead and bought a lot of German, British, and many other, auto ancillary companies for peanuts, because things were bad. And by buying those companies, suddenly you have an ecosystem today after 10, 15 years in India, where Indian auto component suppliers are supplying to the Mercedes, to the Audis, to the BMWs, to the Fords, everybody in the world in a large way, because you could take this beachhead, quickly jumpstart into the technology in many areas, and then really build a large business. So we need to think of the same thing in all others. Semiconductors, for example. You start building a fabless semiconductor chip company. It'll take 3, 4 years to get the chip. You'll have one chip. Who's going to be using the design? How much scale do you need in terms of making a viable chip company? You need a whole series of things. And unless you think about all of that, it'll be a wasted effort and a bunch of frustrated entrepreneurs saying, I did all this stuff and nothing went. So I think we've got to think very differently to jumpstarting all of that, right? And I have some suggestions in terms of what are our assets. Why can we, in an ethical and nice way, get all of this done from the world, right? The government policies aren't moving fast enough. So while we're talking about things, we aren't acting fast enough and not realizing that we are also fighting against time. So for example, the sense of urgency and decisive that is needed, still not there. We are still happy or content with attracting low-end manufacturing jobs. If someone says, oh, I'm producing manufacturing iPhones in India, it's good enough. It isn't. I think we need to change that. And the incumbents, by the way, the last part I also wanted to highlight very importantly, all the Western world companies, 30% of their global business used to be in China. Tech companies I'm talking. And all of that is going to become zero or low single digits in the next 2 years, 24 months. China has already had a saying that I'm going to buy everything in-house, all in China. That's what they call. So where will that 30% business of the rest of the world come to? India. So everybody wants to come and sell to India. So why everybody in the world is being nice to India today is because we are the market that is going to make those companies survive. Imagine all tech companies in the US suddenly have a 30% degrowth in sales. How many hundreds of trillions of dollars of economic value add will get eroded there? So they are saying, let's come to India. So the president of the US will come, the companies will come, everybody will be very nice to the Indian politics, the Indian businesses, because they want to sell. Okay? Second thing, China's stated strategies, first I build the technology, mature it in China, then I go to the world. So if you've been reading the newspapers, there's tremendous pressure for Chinese company to set up joint ventures, ecosystems in India. So we're going to have a double barrel attack where ready-made products of everything that we want to do will be available either from the West or from China at the lowest cost, and then we'll be in the same dilemma. Hey, why should I build this here? I can get it for a cheaper from somewhere, perfectly ready. And this is the dilemma we've been facing for the last 50, 60 years. And this is going to accelerate in the next 2 to 3 years. And we better do something about it, right? So anyway, just to put things on the other side, but if you do the market cap of the top 10 listed US companies today, 8 out of 10 today are tech companies. They are not your natural resources, they are not your manufacturing, they are not your services companies. Whereas 0 out of 10 top 10 market companies in India are there. This is how things have changed. So we better realize this is the change which is coming. This is something we need to do about it. And if you don't, what is the price we're going to pay, right? So what are the strengths? I will not go into the details of the strengths. We all know about the talent part, which is great. The only thing I wanted to highlight is we have not leveraged our Indian diaspora well enough. I think when the states, each state goes out with their, attract talent to, US, and I think they should go and attract that talent of that state and say, please come and start doing product startups, because those guys have the muscle memory, they have the experience of building successful tech startups, going from both business and technology. So I think the states, rather than asking for investment, they should say, I'll set up a 1,000 crore fund to attract the best Kannadigas in the world. Come back and tell me what startups you can do. I'll do whatever you want. I think that's the kind of approach we need to take differently in terms of tapping that diaspora. We have a great home market. We say, oh, large market. When have we extracted our pound of flesh for asking a foreign company to sell in India? Why I want to be saying that I want all these 20 pieces of technology to be given to Indian companies, so that the question I raised in the previous slide about jump-starting the tech ecosystem. This is our way. If you want to sell in India, I want all of these background technologies, all these standard essential patents, all these IPR to be given to me on a France basis, or done a technology transfer in India, so that I become, in 2-4 years, self-reliant, at least from that background stuff. I jumpstart my ecosystem, and in return, I'm happy to give you that market. But if you give the market on a platter, China did that. So I think we don't need to, kind of do it in a negative way. I think we should do it in a positive way, that this is our rule of the game. Please come and play by it. And this is why I'm doing it. So I think this is what we really feel we need to leverage our market access. And we have so far been giving our Indian market on a platter to anybody. And in fact, we feel happy. Oh, now suddenly Tesla is going to sell a car in India. Great. I think we should say, okay, you sell a car, but I want these 25 pieces of technology to be, given to Indian companies so that we start learning and then we can build on top of it, right? Geopolitical advantage is clearly in our favor, because world is looking for a non-US, non-China source. And I think we, as a leader of the global South, absolutely have an opportunity to take that place. Technology is, again, in fact, Professor Debrat is here. The kind of, so his team is doing something called MOSIP, which is the equivalent of Aadhaar for international things. 100 million, subscriber or rather users have signed up on that MOSIP platform. And it is being done at IIIT Bangalore under the radar kind of a situation. So that is a concrete example of the, 23 countries. That's a concrete example that world wants, a lot of the global South wants a tech from India, which can be trusted, which can be long-term. And I think this is a great opportunity for us, right? The next one I think is a very interesting thought again. Aging economies. So if you look at Japan, Korea, Taiwan, let's just talk of these three. The average age is, 50 plus, going to 60s. I have, people and businesses in Japan that I know. There's a ton of technology available in Japan. Display technologies, lithium-ion battery technologies, which was developed by people who are now in the late 50s and 60s. There aren't enough technical people in Japan to take over that technology. And in 5 years from today, those technologies will go into lab, optical, by the way, tons of research done. There's nobody to even own and keep that technology alive. And if India can say, you know what, I have a $15 billion trade deficit with Korea, 25 with Japan, 30 with Taiwan or whatever, let's kind of at a country level do a G2G deal where India provides the technology manpower base, we absorb the technology, and this ecosystem, not the Chinese ecosystem, the aging economy plus India ecosystem competes as a third force which really becomes a global play, and we can jumpstart all this technology. Korea has the same problem. Taiwan has the same problem. So why can't we work with those countries rather than going after China and saying, okay, and China, by the way, got all these technologies from the same countries. So go to the source. Why do you have to go to the middleman here, right? I think so this is something which has to be driven from the absolute top. So in fact, I was telling that every ambassador in the country of India should have a cheat sheet. What exactly does he want from Japan? In which area? So what does he want in space? What does he want in electronics? What does he want in semiconductors? What does he want in EVs? And we need to, when our senior leadership goes to those countries, we should be clearly saying, these are the 4 things I want from Japan, and in return I'm going to be giving you this market access in India, and let's work together, and this is why it's good for you. I think somewhere that kind of a thought process has to come into the leadership in the country, right? The good news is efficiencies in execution. I think the whole, the digital public infrastructure that we have created, the Aadhaar, the mobile, the financial inclusion, the GSTN network, see, this is a very efficient infrastructure for doing anything. Businesses, technologies, whatever. US doesn't have as an efficient as infrastructure like this. Japan doesn't have it, Korea doesn't have it, Taiwan doesn't, nobody in the world has it. So I think this efficiency which we have created has to be leveraged for much, much better use, right? And of course the government support, we're all committed to Atmanirbhar agenda, which is good. For example, we talked about the Tejas and 4G and 5G. We were an optical networking company for 2000 till 2018-19. But we know we can build anything. I mean, you want us to build the most complex equipment, we'll build it. The problem was, after I build it, who's going to buy? So in post the Galwan Valley, whatever happened, the top leadership said that, okay, why can't we build our own 4G, 5G equipment? And we said, sure, we'll build it. And I think you were probably there in a few meetings. I said, I just need 18 months, And bang, within 18 months, we built a world-class system in the same trial network where in the same 50 sites, there was a Nokia base station, there was a Huawei base station, we put and within a period of 6 months, we fine-tuned it and did it so that the KPIs or the key performance indicators were as good, in many cases better than those guys. So here was a concrete example where when the countries, so now let me give you the economic case of all of this. So the country in 2019 had 2 choices. A $2 billion order could have been given to BSNL. They would have bought Huawei or whatever at a, whatever price X. And, they would have been, hopefully, they would have said they would have executed and been in competition with Jio and Airtel and all that. But India already had 4G, 5G, so we didn't miss out as a country. That was one approach. The other approach is, let's give a chance to an Indian company. So the same $2 billion, instead of going abroad, came to us. We created a complete technology, and we are now the 4th country in the world which has the entire 4G, 5G, and the entire communication stack. We do around 30 to 40% value addition in the country, so 2 billion times 40%, so $800 million retained in the country versus 2 billion would have gone outside the country. So country is net positive on $800 million. We created a $3 billion company. My market cap was probably about less than $1 billion in things, so we created $2 billion of economic ads. So a simple action has created a $2.5 billion net positive for the economy without doing anything. And now when we start exporting to the world, why can't we do this thing in other sectors as well? So the whole point is, oh, I'm getting cheaper, someone is giving me today. I don't think we have lost the country's edge in terms of technology absorption. We have not lost a single rupee of taxpayers' money. And we have gained out of the economy. And all it was taking so I think someone needs to look at the totality of the economic decision rather than in this tender L1 by 1 rupees, is the game. I think this mindset has to fundamentally change across sectors in the economy, which is how we will progress. So all the elements are there, but then what's the recipe? That's the next question, right? So in my mind, we need a focused approach. We can't do everything in all the sectors. As we said, we have limited time, so we need to pick and choose the battles we want to fight, right? So I think which battles we want to fight. So I think to me there are a few traits we need to look at which problem to solve. The first and foremost is it should be a large market. You don't want to solve which is a 100 million problem, because even if you are the best in a $100 million problem, it's not big enough. So it's worth solving problems which are tens or $100 billion in size. Not just in India. So India is a good market, but globally as well. It should be strategically important for the reason that we discussed earlier. And third is an interesting thing, going through a technology disruption cycle. So when the technology changes, it kind of really resets the clock for almost everybody else, right? Because it's no longer that someone who's been an incumbent for 20 years continues to have the advantage. So I think things which are going through a new standards process, for example, a new use case scenario, or like in the case of electric mobility, it's a, from ICE to electric mobility, there's a different thing. So I think that's a good one to look at. Fourth one is very interesting, India-specific use cases. So India is a very unique country. For example, medical devices or technologies. There are many ways India works which is different than how the rest of the world works. But I think India-specific use cases give us a first-hand visibility into what kind of innovations are needed. So our product developers can talk to the customers and really create new solutions which nobody else sees it. So a US guy, for example, doesn't see that you need to develop a product for $2 or $5, right? He sees I have to develop a $100 product. So in fact, many of you might be aware of that MIT had a program many years back, one laptop per child, and they said, oh, African people need all of these cheap laptops. But what their definition of cheap and cost effective, I mean, is 10 times what really the affordability is. So I think the perspective we have in India is very different, right? And I think the way today I feel is it's all about systems. It's no longer about hardware alone. It's no longer about software alone. And so I think there are different elements of hardware plus software plus manufacturing. And I think that's a unique combination we should try to exploit. So I think things which have elements, some or all of it in some proportion, are good candidates. So the candidates I feel is electronics, telecom, semiconductors, particularly fabless. I think is a good starting point. Aerospace and defense, Dr. Kiran Kumar is there. I don't need to talk more about it, but that's a whole new frontier opening up for a variety of applications which it was originally not even thought. Defense, clearly, if we can't protect ourselves, nobody will for us, and I think there's enough progress we've made. Autonomous vehicles, we're discussing, for example, in the context of drones, right? Just look at it this way, that the air traffic controller, which was created 50, 60, 70 years back for, controlling airplanes, right? The drone ecosystem has, 10 times, 100 times, 1,000 times, or a million times more vehicles flying around. What is the equivalent of that air traffic controller for drones? Who in the world is working on it? What's the standard? And there aren't enough. So can we take a leadership in some of those areas, create things here? The way that traditional warfare was fought, and now if you see the Ukraine war, I mean, the large drones aren't needed, those are actually bad ideas, right? So in the smaller drones category, which is where India focused, why can't we do something very unique? Because it's again the same thing. Sorry? You need to add agri-tech. Yeah, so agri-tech, I'm sure there are a lot of areas, but my whole point is that we need to look at things which make sense for India, where there's a lot of benefit, and we create products around it. That's how we want to start off, right? And we have to think of an ecosystem approach.
So Sanjay, why would you, in your opinion, consider semiconductors as fabless?
So fabless is because the fab, okay, so there's a longer discussion if I were to, I'm also mindful of the time, by the way, so we'll discuss it in the, we'll discuss it in breaks, but I just want to be mindful of the time unless you be generous with me and give me a few more minutes, which I can. Okay, so my point is, we'll come to that, but I really feel that some of these are horizontal things which we just have to do. My point is, where do we have a right to win? Where do we have a chance to success? And again, frame it with a 10-year mindset. Everything is great when you have infinite time, which we don't. So let's focus on things which make sense right now, right? So again, I've put something, but the approach is the different. See, approach we have to take is, it has to be an ecosystem approach. The problem is, we all think that everything will happen in MSMEs and startups. Unfortunately, that's wrong. Things happen when you create global scale companies. And in fact, if you see the top 5 companies in any sector in the world, take 90% of the profits and 80% of the revenues. Any sector you take. So unless we get into a top 5, you will not create enough economic value add to be able to fund the rest of the ecosystem. So creating a whole bunch of MSMEs and startups is not going to solve the problem. You got to create these big motherships. Like ISRO is the mothership, for example, for the space. Around ISRO, you can build lots of startups. But imagine if ISRO didn't exist, and then you start creating a bunch of startups, where will we be in space? If suppose Tejas can potentially become a mothership, that can be a foundation for acquiring a lot of startups and putting together things which otherwise may not be possible. Okay, so that's one. Secondly, the academia. See, academia, and in fact, I'm also part of one of the things I've been working with Professor Bhatta also, that this whole national mission for cyber physical systems, right? So I see academics and government put 3,000 crores for that project. The academics are working in their own world. Industry needs a separate set of problems. Why aren't we tying this up together? So I think what is needed is a systems approach. You take, these are the 5 or 10, I'm not advocating these are the absolute right list, there could be plus or minus, but take that as a system level problem. Say what are the things we need in the systems? What are the subcomponents? Where do we need to do fundamental research? And someone needs to orchestrate and tie it all together as a CTO of the country, if I were to say this, all of this needs to happen. And then we farm out the problem to the academician in the language he understands. Say, I need a better image processing algorithm which will do so many frames per second with so much less power and with so much accuracy, and give me this, and these are the... He will do that for you. But if you say, build me a better drone, and he doesn't even know where to start. So I think I would not blame the academicians, I would not blame the industry. I think it's just the way we have structured things needs to be fixed, right? And the government. So government is very happy funding, and I have some specific recommendations. We'll fund, DRDO, Dr. Nayak is here, but DRDO ko jitna paisa chahiye, we'll give it to you. IITs, IISc, triple IT, what money you want, safe bet. CDOT, CDAC, safe bet. But if all of that had not worked for 50 years, let's admit it. It's private sector and entrepreneur and the best minds who have to come together and do it. So let's figure out a way to get a lot of government funding to the right set of people who will make things happen. And we are not the first ones in the world doing this. US, for example, signed up a $60 billion CHIPS Act. They're giving $60 billion to private sector companies to go build stuff. China has probably given $100 billion to Huawei alone. Forget about other things, right? UK is giving money to their companies. The world is giving. So why in India, in government, shying away to fund private sector, which is actually going to deliver results in business and so on. So I think we've got to take an approach on that. And as I said, look at the whole value chain things. Don't stop at the first level system that, so if you see today in the electric vehicles, we say, oh, we are producing, two-wheelers, we are producing four-wheelers. Go ask, where are you buying the batteries? Where are you buying the motors? Where are you buying the control chips? Everything is coming, so we are all assemblers. So I think unless we go down and say, why can't we build a motor with a certain kind of frequency, certain kind of efficiency and so on? It's not rocket science. We can do it. Understand we have challenges in terms of chemistries of different lithium-ion batteries and so on. But why can't we talk to Japan and take from Panasonic the absolute, very nice technology and say that I use that as a starting point, or take some new chemistry and build that. So I think those are the kind of thought processes which have to come, because if we don't, we're not going to get there. But building companies of scale has to be the fundamental thought process, and the rest of the ecosystem has to work. So anyway, so what's the playbook in terms of what do we need to do? If I were to quickly summarize, the government really has to put significant amount of money. I think in this current year's budget, there was a good start. They announced 100,000 crores innovation fund. I think there is a thought process which some of us are trying to also advocate, that a lot of that has to be coming into private sector. It should not be restricted by the government rules and regulations and GFRs and everything else. It has to change, number one. And you have to fund from R&D to successful commercialization. We're very happy to fund the R&D aspect. Okay, you product banalo, you create this prototype. We will have a museum of prototypes and little stuff in the country which doesn't scale. And that's not exciting. Entrepreneurs will not do it again, because if they... So we have to look at all. So really we have to give incentives for product development, production linked incentive, which is for removing your handicap because you're on economies of scale problem. So you get while you're producing, you get the delta for that. And then give the incentives to the buyers, that if you buy an Indian product, you get 10% less from the government. Because Otherwise, we'll be in a chicken and egg problem that, oh, you didn't meet the L1 and I'm not there, right? Similarly, everybody needs to work together, as I said earlier. Supporting government policies is very, very crucial today. See, the world is today no longer the WTO world that we've all been programmed to think that, oh, WTO will not, the WTO is dysfunctional anyway, right? So I think we need to see what every country in the world is saying, what is good for their country first, right? And I think for India, we need to start thinking like that. The market power that we have is our biggest asset. We can dictate what we want from anybody in the world, and people will ply. I can guarantee that. Except that in business or in any negotiation, you never get anything till you ask, right? So we have got to be bold enough in asking what we want. And I think we need to use our Indian market, use tariff and non-tariff barriers effectively. So if Indian products are available, there's nothing preventing you to put customs duties of a certain kind. US just a few months back put 40-50% duties on EVs from China. So where's this WTO and that too for protecting a company like Tesla? So we are not even 1/100th of that scale. So I think we should think of the tariff barriers and non-tariff barriers and fiscal incentives we already talked. And again, this thing again comes back to the point is that whenever, this is more of an economist / a planner problem, is that when we look at things, we only look at we don't look at the full stack problem. We look at the one particular element, say, oh, I'm getting an expensive product here. But you don't look at, if I look at the entire value chain, is the country saving or the country going on the negative or positive? And trust me, once we start doing that analysis, the answers become obvious in terms of what we got to do, right? Jump-starting the product ecosystem, I think we already discussed how to quickly get technologies from the aging economies and friendly countries and getting the, our Indian diaspora. I think that is, in my mind, that is because when I talk to a lot of my friends of my age who've been working in the US, very successful people, they're all waiting for a real opportunity with a real, support in the country to come and do something like what you're doing with Sage in Bangalore. I think there's equivalent of that potential / passion available for others, except that we're not tapping it. The entire semiconductor industry in Taiwan, came out of people from US who chose to go back to Taiwan, set up in the Hsinchu high-tech city, TSMC was set up, ditto happened in China. We haven't done that effectively in India. We are very happy with, dance drama going, soft Bollywood going, and connecting with the Indian diaspora. Let's get the deep tech connects in a much bigger way, right? Ecosystem approach I already talked about, and the last part is again important. Assuming, we are able to get the products done, assuming we are able to get, successes in India, we've got to go to global scale and look at what China does. China, for example, for Huawei, again, since I'm familiar with that industry, at every point in time when there was a global economic crisis, like in 2007, Chinese government gave $30 billion of lines of credit to Huawei, go and distribute that to African countries who want to buy Huawei equipment. So if you're an African country, you say, okay, you get an interest-free loan for 5 years, buy this Chinese product, that's what it is. If you look at a lot of the metro projects in the country, JICA is funding, Japan, funding agency. But in return, they, of course, push the Japanese products who come as a part of the funding. So I think we've got to really do export promotion, whereas where do we give our lines of credit? For rice export, for creating a parliament building in some countries, which are all fine. But I think now we've got to promote, deep tech, high tech exports because they have stickiness. You've set a network once, it's going to get upgraded second time, third times, forever, right? So I think we've got to think like that. Branding of India as a product nation doesn't exist. You ask anybody in the world, and I firsthand faced problems in Tejas. We are selling in 75 countries. We could get $10, $20 million deals. To get a $100 million deal, to get a $1 billion deal, the first question they ask is, do you make products in India? Services, yes, you want to give IT services, no problems. There is no, by the way, I was surprised, there's no Indian product of any industry, I'm not talking of tech, which is a global product. We don't even have a garment brand, which is a global brand, whereas you can say, there are so many designer brands from the world which are there. So I think when we created this vision for Make in India and all the things, and there was a big, concerted effort, I think we need similar effort for branding India as a product nation. Because without that branding, the sales follows the marketing, right? So you got to create the marketing cover to be able to sell that. And then, of course, G2G relationships, I think we need to really play much more into economy, much more into technology, both for inbound technology, outbound things, and you really, get all of this going. And I'm pretty sure that, if you do all this, it's fantastic time. I think we have to do it. In my mind, I think with a lot of the experience and all the hard work we did over the years, we have a good learning that I was trying to articulate as to what has to be done, because it's very easy to talk about problems. It's a little bit harder to give the solution. So hopefully, I've been able to, put together some of the thoughts, and it would stimulate a little bit of thought process among all of us to get to the next stage. Thank you again.
Thank you very much, sir, for your insightful and engaging speech. It was indeed a thought-provoking session for us to know how we were only consumers and service providers. And we also were excited to know the opportunities for India to be a technology product nation. Thank you very much, sir. So as a token of appreciation, I would request Dr. Prashant Shastry to honor Mr. Sanjay Nayak. Meanwhile, participants, if you have any queries or if you want to discuss anything with sir, we are open to have some discussion. Yeah.
Just a comment. This top-down design, top-down approach is very, very important, and that's what we have been trying to promote. Always look at the whole system as a whole, and then go from there. That's a very good approach in education. Thank you.
The SAGE inauguration ceremony has come to an end. We thank you all for your presence and participation. We now embark on a new journey as we launch the first SAGE International Symposium on Advances in Wireless Technologies. So ladies and gentlemen, as we continue with today's exciting program, it is my pleasure to invite the first speaker of the symposium for our symposium today. Please join me in welcoming Ms. Aparna, who will be introducing our distinguished speaker, Dr. Kiran Kuchi, for the next session.
Hello, everyone. I would like to introduce our first speaker, Professor Kiran Kuchi. He's from IIT Hyderabad. Professor Kiran Kuchi has lived in USA between 1995 and 2008 before he moved back to India to join the IIT system. He holds a master's and PhD degree in electrical engineering from the University of Texas, Arlington. Professor Kuchi currently holds a position as a professor within the Department of Electrical Engineering at the IIT Hyderabad. He spearheads research and standardization endeavors for 5G advanced and 6G technologies on behalf of India at the International Standards Organization, focused on shaping future communication systems. With a prolific portfolio, Professor Kuchi boasts over 200 international patents, including some recognized as essential standards for the 5G. Notably, he is also the founder of YSIG Networks Private Limited, which is a venture incubated at IIT Hyderabad, where collaborative efforts between IIT Hyderabad and YSIG have led to the development and commercialization of 5G base station and user equipment technologies, as well as narrowband IoT system on chip solutions. Unfortunately, he is not here in person to join us. He was not well. He couldn't travel to Bangalore yesterday. But he would be, however, giving the presentation through Zoom. So I invite him to give the talk on advancing from 5G to 6G, the future connectivity. Please welcome Dr. Kiran Kuchi.
Can you hear me? I hope you are able to hear. Hello? Hello?
Yeah, it's visible, sir. Your screen is visible.
Can you hear me also?
Yeah, we can hear you.
Thank you. My apologies, I got a little under the weather this morning, couldn't travel. My sincere appreciation for for giving me a chance to speak at this important event. I will talk about the importance of RF and microwave and this excellent effort during the course of my presentation. I think it's a very, very important initiative, in my opinion. So let me get started with my presentation. This is a bit more technical in nature, but also I will try to relate to the previous talks as much as I can. Today I will talk about the future evolution or the evolution of wireless communications, especially cellular wireless communication technologies. 5G has been rolled out. I think in a few years we'll have a very stable and useful 5G connectivity and the associated applications. It's still an evolving deployment. And India, as Sanjay has spoken, has embarked on a journey of indigenization, and he has really championed the cause in this space. But I think we have a lot more work to do. And the previous speakers talked about the importance of technology and having this long-term view in place. For what we intend to do and position the country, whatever height we want to reach in the next 10, 15, 20 years. So I am presenting a slide with a very long horizon, time horizon, a project it started in 2020, where we are going to complete this project in 2030. Usually we don't come across such projects, with such a long time horizon. And it's worthwhile, to talk about this important initiative at International Telecommunication Union, ITU, who is responsible for defining wireless communication standards. And member states are the primary stakeholders in this process. Of course, industry will be driving the efforts in the background. Right now, 5G is evolving towards its next generation, and we call it 6G. That's a commercial name, but ITU calls it IMT 2030. That's a formal name for 6G. And a vision and framework for this future connectivity has been laid down by ITU about a year ago. And India has taken a very active role for the first time in defining this vision, which will, I think, lead to development of the associated requirements, including India-specific requirements, and also standards with our own technology footprint in place. So I'll talk about these timelines in a bit, but I want to share with you some important developments. Most of these are, behind the scenes activities. I think the previous speakers talked about, the other countries coming to India, being nice to India, wanting to do business in India. I could really experience this at least firsthand in this ITU forum. In this meeting concluded in Geneva, June 2023, where the vision document was published. It was an important event in this 6G journey. India had, I think, about 10 people who represented both from industry, academia, and government. And we are sitting in the front row, as you can see, a few of us, along with the American delegates and others. And for the first time, we were able to introduce and some of the important requirements that stem from in our region and our country into the 6G definition. Those who are familiar with 5G, you heard of this so-called enhanced mobile broadband services and Internet of Things called massive machine type communications. All these essential elements of 5G are still preserved in the 5G evolution towards 6G. And this nice diagram has been worked out as a result of 2 years of very intense efforts among member states and the contributing companies. And the one with the flag, the tricolor here, a dot has been introduced called ubiquitous connectivity. It is essentially going to be one of the pillars of the 6G definition. It's not every day that the Western world will give you a chance to introduce and influence the evolution of such an important global effort. Nevertheless, we managed to accomplish this critical feat. A lot of work has gone in the background. I think the respective governments from different regions, a lot of back channeling and industry, academia played a very important role. I was more of a facilitator in this initiative. What I would like to say is that the world is looking to India to actually take an active role in these developments. There will be push and pulls, but the fact is that there is a seat at the table, and it's our chance and it's our time from this region to make the impact. So we need to get our funding together, our efforts together, our act together, and make use of this opportunity to make this deep impact that we envisage to create. Let me go back to the technical aspects of this 6G. Every dot here, represents a new usage scenario. The global standards are built around these important usage scenarios. Think of them as new services that you can expect. And the next effort will be defining the technical requirements. That is basically the performance requirements associated with each of these usage scenarios over the next 2 years. Then standards get developed, to meet those critical requirements. And in these new usage scenarios, as wireless evolves into 2030, and maybe these new standards will get deployed in 2035 timeframe, they'll be operational until 2045. Look at the time horizon. We're taking such a long-term view, and several new things are bound to happen. While it's never easy to predict the future and what use cases we might end up using, but the trend is apparent. When this diagram was created and this vision was published. One of the most important ones here is, apart from ubiquitous connectivity that I'll talk about in a moment, is immersive communication. So the broadband is going to evolve to include immersiveness in all aspects of communication. Excuse me. And the second aspect is there is a great talk about a lot of noise made about integrating AI and communication at various levels, whether it is at a device level or a chipset level or a network level or a radio communication level. There are various ways in which this could be done, but there are a lot of effort ongoing, and this marriage between AI and communication, and Dr. Kiran Kumar talked about control. Intelligence, communication, and control. Well, it's as old as 50 years. This concept, and this is becoming more and more pronounced, and getting into wireless communications in a very significant manner. Yet another important development is introducing the notion of sensing into communication. This sounds like this sounds like what can this sounds like a very new approach, but actually it has been around. One example is one form of sensing is radar. It has been around so long. What's happening is that, which is also related to the theme of today's event, training people in RF and microwave systems. The wireless communication systems are moving more and more into higher frequency range, especially above 6 gigahertz and 10 gigahertz range. And there are a lot of efforts in even higher frequency range in millimeter wave and beyond. And in most of these systems, there's going to be immense amount of complexity introduced in the RF circuits. That is to say that to get the wireless signals to go through the windows and maybe get around the buildings and get their adequate coverage, one needs to have one needs to rely on probably that's the only choice, a large number of antenna elements. As it turns out that 5G today, as it is deployed, already incorporates about 200 antenna elements in one sector, what they call, in one cell. But I think this is going to expand at least tenfold as we move into higher frequency range, and the RF circuits are going to become extremely complex. There are already efforts to build, digital beamforming, analog beamforming, hybrid beamforming circuits. Very precise alignment between RF circuits is required to make this happen, to achieve precise beamforming, which has been done in radar world. So radar is actually moving into the 5G base station. That's one example of the sensing moving into communication, but probably there are other examples of integrated sensing and communication. But this is going to be a reality sooner than later. And then the discussion is incomplete without talking about satellites. In ITU Working Party 5D, which is responsible for terrestrial standards, a whole bunch of people from satellite community, they came and contributed, and they made substantial efforts to introduce satellite as an integral part of 6G. Well, there's a lot of push and pull in these two communities, that is terrestrial community and the satellite community, but nevertheless a compromise has been struck. That is to say that satellite communication, especially including HAPS, LEO and GEO orbits, and usage of such satellite connectivity will be part of the 6G vision, but only as an interworking system. That is to say, the technical parameters and specifications built for 6G will not include satellite, but satellite systems are expected to interwork with 5G systems.
Sir?
Some of you may already know that 5G standards already include support for satellite connectivity by leveraging the chips and circuits that are built for terrestrial, and
Sir,
through software
excuse me, sir?
modification you can.
Is there
Yes,
any
yeah.
slides getting changed, because we are having only the same slide?
I'm on the same slide, yeah.
Yes, sir. Thank you, sir.
No issue. Thank you. Pardon me for a long discussion around one slide, but I think that those who are involved in terrestrial and satellite community will appreciate that this merger is happening at a device level and also at standards level. But the critical point is that 5G standards are already being leveraged for dual purpose. That is at the device level, as well as as onboard satellite modems on the transponders or ground-based systems. 5G is being leveraged, and it will evolve into 6G with satellite connectivity. I will spare a few moments about some technical aspects of the future connectivity. When 5G was introduced, critical parameters like latency, mobility, data rate, spectrum efficiency, there's a lot of emphasis on that, and it continues to be there, spectrum being limited and scarce. New capabilities have been introduced in 6G. Of these two new capabilities, two came from India, whether it is operators or academia or government. One is trying to achieve as much coverage as possible, including large cells and expanded rural connectivity and even enhancements to urban connectivity. Interestingly, coverage was never a scientifically measured parameter as per ITU capabilities, and there was a lot of resistance to introduce that, but we managed to do that from India. And there is also a substantial contribution from the Indian delegation that is called interoperability. Some of you may be familiar with the concept called Open RAN, that is exploiting open interfaces between different parts of the radio communication systems and different subsystems can be built by smaller entities or even larger entities. And by introducing interoperability and open standards, the cost of deployment of the system can be reduced substantially. This initiative has taken a new lease of life. It's been around for 5 years or so, or more longer in the United States. Most of the global operators are beginning to embrace this interface interoperability, so-called Open RAN standards. But 6G, as you can see from this figure, adopts this interoperability as a capability of IMT 2030. So this openness is codified into 6G standards. So this will have a significant implication going forward into 2030 and beyond. There is a great focus on energy efficiency, making radios energy efficient, especially when you have thousands of antenna elements and a large number of RF chains using analog beamforming or digital beamforming. So the energy efficiency has been talked about quite a bit, and other AI-related capabilities which are yet to be defined. So in summary, I put some timelines here. 2024 to 25, the next 2 years will be the focus at ITU on the technical performance definition. And there is a body called 3GPP, that defines technical performance, technical specifications, standards such as 4G and even 5G today that we use. Activities will begin to happen in this body as early as Q2 of next year. There will be a parallel effort between 3GPP and the SDOs such as TSDSI and others. And these efforts will happen in parallel, resulting in a specification also which leads to a standard around the time 2029 and 2030. The reason why I place the emphasis on these timelines is that this is an opportunity, and and it has to be cashed, that is exploited by India, that requires a substantial investments into this new technology. This requires significant R&D funding, focused R&D funding, and aligned with these timelines. If you don't do that in the next 6 months or 1 year, and I think this is a bus we'll surely miss. That's the point I want to drive home. So where we stand today in terms of 6G R&D output, this 6G is too far, that we recognize, 2030, 2035. But I think the best we can do is count our efforts, measure our efforts in the last 5 to 10 years in the 5G standards creation, and see where we are, and then put a target for ourselves where we want to be in terms of outputs for these standards. There were about 500 technical papers submitted to 5G standards. There were some efforts to create indigenous technology, and some standards of essential patents have been declared to TSDSI. But the number of people that contributed to this entire effort, at least those who actually went to the meetings, is less, just about 10 people. And this number has is increased, now about 20 people. These are experts. They go to different international meetings and contribute. But this is a very small number compared to the number of people coming from just one company like either Huawei or Qualcomm or anybody else. So we should be looking at 200 people rather than 20 people. So there is a 10x increase required in the number of experts that we want to send there. Of course, every expert going to these meetings needs at least 5 or 6 people, scientists, backing them with doing research and simulations and prototyping, whatnot. So the number of standard essential patents declared to TSDSI is much less than 1% of the global share. Usually, this is not something you can easily measure, the standard essential patent. They'll run into a few hundreds, 4G plus 5G combined, but 12 declarations is very small output compared to the global share. In order to achieve this, the vision led by the government, especially Department of Telecommunication, It has been said multiple times that we should aim for 10% of the global share, but also this requires a 10x improvement in whether it is funding, whether it is the number of people that we have to train. So this brings the issue of manpower. It turns out that in this particular field, I classify them as two kinds of engineers. One is the digital signal processing engineers. I mean, just they work on digital, and there are people who work on analog aspects, like what Sage is trying to create the manpower. The number of people available is in this country at this time, is quite low in my opinion. But there are a lot of people, but they're all locked in some MNCs, and I don't think they're available easily to small companies or large companies of indigenous in nature. So I think we have to really take a very serious view of the current situation and act on the funding and creation of manpower. I will not talk about the technical aspects of this deeper technical aspects, given the limited time available. But I will try to stop here and close my presentation. Thank you very much.
Thank you, Dr. Kiran Kumar, for that truly enlightening and inspiring talk. So, is there any questions or anything to be discussed? Anybody? Any questions? Yeah, 1 second, sir. So, there is some questions. I'll just pass on the mic to them.
If you could repeat the question to me, because I'm not able to hear, I will appreciate that. Yeah.
Hello.
Yes, sir.
Yeah. So Sanjay Muge, very nice presentation. Question I had was, can you talk about the spectrum allocations and so on, and how that is proceeding? And as you go to higher frequency, then the distance over which the signal goes becomes less and less. So how those issues are addressed? If you can comment on those things.
Yeah, this is the holy grail for future connectivity and synthesis. Dr. Nayak has talked about in the 80s he worked on 35 gigahertz frequencies, and they went up to 90. And 5G was very ambitious in bringing the 35 gigahertz to cellular usage. There was a very ambitious effort to use millimeter wave frequencies, put this technology into the smartphone. But as we all know, it doesn't work in the smartphones. So what is that needs to be done in 5G? First of all, I think we have enough work to do to improve the coverage in so-called 3.3 to 3.7 gigahertz mid-band. 5G coverage I think is highly questionable. Either the operators invest huge amount of money, create a lot more towers, which is really difficult. Otherwise, we have an issue, at least in the uplink direction, that is the speeds are so asymmetric. If you drive around, do a speed test, which I do quite often, and we have a system we developed. We also drive test in IIT Hyderabad campus every day with our own system. We get speeds on the order of, on average 100 megabits per second, or even, up to, close to 700, 800, even a gigabit per second, if you get lucky. But on the phone to base station, the speeds are, at times at 20 Mbps, but it can also become kilobits per second. So there is a serious problem with spectrum. This requires technology to solve this problem. One is at least in the 3 to 4 gigahertz range. One has to use lots of antenna elements. Antennas and RF is going to be the future for the next 10-20 years. But to answer your precise question, what is 6G frequency? 6.425 to 7.125 gigahertz is likely to be allocated in India, and China is moving the same direction. But if we have issues with making the system robust at 3 to 4 gigahertz, you have to do a lot more work and hard work to make the system work at 6 and 7 gigahertz. So a lot of research is required, and it's going to be a tall order. United States doesn't have this 6.425 to 7.25 gigahertz spectrum. They already delicensed it for license exempt access. We call it Wi-Fi. They also don't have good amount of spectrum in 7 to 8 gigahertz because that's occupied by defense. So there's a lot of effort in working on 7 gigahertz, 8 gigahertz, up to 10 gigahertz, going all the way to X-band. So these are not conducive to cell phone reception. I think new architectures have to emerge. A cell tower giving service to phone. I think this concept will probably work till only at best to 4 gigahertz. Maybe at up to 6 gigahertz if you get lucky. But beyond that, new network topologies have to come in. But the efforts to use these higher frequencies, 6, 7, 8 gigahertz, there are a lot of efforts going on. That's what we call 6G frequency band. There are no good frequencies available beyond 4 gigahertz.
Does this work? Yes. Professor Kiran, this is Satish Kulkarni. Although I work for Juniper Networks now, I was with CDOT for 17 years with Dr. Kori. So first of all, I would really like to compliment you on the presentation on the fact that India has a footprint in determining the standards for IMT 2030 plus. It's a non-trivial achievement. I think many of us have tried to influence ITU to get standards relevant for India's unique topology, and I think this is very, very nice to hear. You've been very modest about this accomplishment, but in my opinion, it's non-trivial. The second thing I would say is, as a result of this accomplishment, this represents a huge opportunity for all the RF companies in India in order to develop our own equipment as it relates to even private 5G or private 6G, in addition to the niche areas of RF technology, which is really the secret sauce for all 5G and 6G, and that's where all the money lies. Much of the other equipment is fairly trivial in terms of it being a mature technology. So I think this seminar and this advances in wireless technology is very relevant for the next few years in telecom for in India. Thank you.
May I respond to that, if I permit? Yeah. Thank you for this generous comment. First of all, there are so many other people who have contributed to this effort, which I should gracefully acknowledge. My friends at IIT Madras, Sanjay Nayak's company, Tejas Networks, Reliance Jio, Academia, MITES, DOT, CDOT. I mean, the list goes on, and Indian Institute of Sciences and other places. It's a large collective effort which has been going on for more than a decade. Few people are aware. But point is that the geopolitical atmosphere and the conditions are prime for India to milk this opportunity. That I sincerely feel. The second point is that if I have some extra money, a good amount of money, I would put my money on building RF systems, very complex RF systems, not necessarily chips, but maybe those who are experts in that, they can do that. There's a good amount of money to be made, building sophisticated, complex RF systems, and they'll have dual purpose. That is not just for communication, but lots of other applications, including radars and military and defense, and you can export in many places. I agree with you. Thank you.
Professor Kiran Kochi, this is Kori here. First, of course, thanks for the excellent presentation, but you skipped the new waveform which you are working. I think probably we didn't have time. We wish we had heard of the new waveform you are developed. I just wanted to ask you about FR1, FR2. We are talking about there is some new FR3. I keep hearing about it. Could you just elaborate on that?
I will do, sir. First, my apologies, I didn't talk about the waveform because I need like 30 minutes to do that. But I can just summarize in one sentence. There is something called OFDM, which is very, very popular, many of you know. And we invented something called, we put a T in the middle, orthogonal time frequency division multiplexing waveform. In its previous avatar, it's adopted in 3GPP. The 5G phones you use actually use a version of this waveform. few people know about it. But we came up with a more general waveform that we think will get get adopted in 6G standards. It's quite likely. We built a whole standard around this waveform, and we are working on. But one of the nice properties of this waveform is related to the focus of today's conversation, which is RF and RF and systems. So this was invented to make the information transmitted close to the PA saturation point, and try to expand coverage and get more output power, or reduce the power consumption of the radio, especially if you have hundreds of RF chains working in tandem. The waveform has its own role to play. Aside that, FR3 refers to a frequency range which I referred to before, 7.125 to 13 gigahertz. It's called frequency range 3. And frequency range 1 is below 6 gigahertz. And there is this little spot, 6.425 to 7.125, kind of part of FR3 that I think India might use. And essentially, FR3 is just above 6 gigahertz, and it just gets into defense bands and ends at X band. This is the frequency, and people have some bitter experience with 29 gigahertz, 35 gigahertz, but there is optimism that perhaps we can succeed in the FR3 frequency range, more so at the lower portion of the FR3, which is 6 to 7 gigahertz range. So we really have a lot of work to do, but that's FR3.
Yeah. Thank you, sir. So there is one more question, sir. Anybody else? Any other questions? Okay. Thank you very much, sir. So we are certain that your talk will really resonate within us for a longer time, and will contribute significantly to our ongoing discussions and endeavors. Once again, we thank you for your remarkable contribution in 5G and 6G, and for being with us today online. So now I think we'll give a round of applause.
Thank you, madam.
Yeah. Thank you, sir. So now it's a time for us to enjoy the delicious and networking lunch at Falcon Cafe. So take a break, connect with fellow attendees, and enjoy the moment. We look forward to seeing you there. So let us all come back and join for the more exciting sessions at 2:30. Thank you. Yes, sir? Yeah, virtually we thank you, and very much, sir. We missed you offline. Yeah, your presence, sir. Yeah. Thank you. Yes, sir. Yes, sir. So now organizing committee with the same team.
I'm okay, I'm okay.
Music off.
So I'm happy and privileged to introduce the next speaker of the session, Dr. Jalil Akhtar. He received his PhD degree in electrical engineering from the Otto von Guericke University of Magdeburg, Germany in 2003. He was a scientist with the Central Electronics Engineering Research Institute, Pilani, India from 94 to 97, where he was involved in the design and development of high-power microwave devices. He was a postdoctoral research scientist and a project leader with the Karlsruhe Institute of Technology, Germany, where he primarily worked in the areas of industrial microwave technology. In 2009, he joined the Department of Electrical Engineering, IIT Kanpur, where he is currently a chair professor. He has supervised more than 20 PhD candidates and over 75 master students for their thesis. He has been the lead investigator for more than 15 projects in various domains of RF and microwave technology. He is presently leading a major project involving establishment of a world-class, fully accredited EMI-EMC test facility at IIT Kanpur, India. So we are honored to have you here, sir.
Okay. So I wish you a good afternoon, and it's my pleasure to be here. And of course, before I start, I would like to thank the organizers, Professor Shastry, and other, even Dr. Nayak, who called me. I mean, once, yeah, we have to come there. So yeah, so I would say it's really a good. It's my pleasure, and also like it's a good environment and good, I would say, initiative, because at the end, industry, academia, and R&D, they have to work together. That is what we agree upon and we converge upon. So today I would like to give a very special topic, RF energy harvesting. So this is not directly wireless power transfer, but it's sort of a very, I would say, futuristic technology where people are trying to find out that whether wireless power systems which are even otherwise there, whether they can be used also to harvest some energy, especially to energize low power devices. That's something a very simple way what we can explain. Scopes are many. So I won't go into very details because they are in published work, but I will just try to give you an overview so that like if you are a student or a newcomer, you understand the potential of the technology, and then accordingly you try to see if you want to start a work, it's worth doing a new research work, if you are a PhD student, something like this. So that is something what I would like to slowly go away. So if I try to go further, how do we, this one? This one, huh? Okay, good. Fine, so this sort of layout, so I won't go into detail. But I would try to give a background. Usually, when we say we have RF energy in the ambient from many sources, our aim is how can we use them to convert into DC to energize devices. Now, there are two systems which are in place, antenna-based, access-based. This is something like, now conventional one, this is something that is a new concept. I would try to explain the both, say that how they can be used in that concept. Okay, now this is something like, it tells you what it is about. So, you have everywhere you have what we call the RF energy, where you have FM tower, TV tower, cell tower, Wi-Fi, Bluetooth, everywhere you have now Wi-Fi. They are being used for specific applications. Now, the idea is, can we use this energy to energize devices? Imagine you have a mobile phone with you. Now, what's the major challenge? That you have to go and you have to charge. Look for, charger anywhere. Imagine a scenario that you have your mobile with inbuilt charger. So while you go roaming, it charges itself. So you don't have to go anywhere for charging. Beautiful concept. There are some challenges, but conceptually, if you see, that's a very good, novel idea. That's why there are people, even in companies, they are trying to work on if that can, work practically, solve a lot of the problems. And if you try to compare, for example, RF with solar or wind energy or something like this, at the end, they are to harvest energy. They are natural, but this is artificial. But the advantage is that, with solar or with wind, from solar energy, there you have dependency. You can work during the day, not in night. Wind energy, you have to work in some areas. On the contrary, it is envisaged that, in the coming years, RF will be everywhere. So everywhere you have RF, RF energy in that band. And so if that can be worked conceptually, we can try to, use them for many applications. That's a simple example, like this we did in the lab. So you have a mobile phone, you pick up your phone, now you have an antenna, rectifier, and LED. LEDs just consume few milliwatt or microwatt. Now, your conventional, as of today, whatever you develop, this RF harvester, this is enough to energize, let's say, a low power LED. Now, in countries like India, we have major problem of even like to energize in the villages, like because you don't have, even the basic electricity. But now we have Wi-Fi, you have cell tower everywhere. If you can use the same cell tower also to at least give, lightening to rural people during night, that's by LED, that is sort of a beautiful idea. Because without using any, well, at least they will be able to see use them during night. That's also another thing which, we should try to work on. And of course, they've done, and the aim is that we should try to make up lighter and environment friendly and so on. So that's something like, and at the same time, if it works better, the way we do for solar, you can also use this to store, like, they have a supercapacitor. So you have RF energy can be converted into DC and can be also used to store energy for future uses. So that's also one aspect what one could try. So motivation is that, if you see like all these applications, so they are, for example, low power applications like microwatt, this watch, 10 microwatt, this LED somewhere of 0.5 milliwatt. So all these, of course, at least up to this point, where you have milliwatt uses for energizing devices, you can explore using this wireless harvester to energize. And you got rid of, all these, what we call the wires. And that's the motivation why people want to work on this. And, you have everywhere sensor network now, IoT devices. Every IoT device has a sensor. Now, one of the bottlenecks which we have is that the sensor devices, they have limited lifespan because of the battery. If you can make these sensor devices self-sustained by integrating with them some kind of, RF harvesting unit, whether it's compact, they can work without any external DC power. And that's something also, that, and you have everywhere where you say medical, so you have medical, health monitoring for civil structures like concrete, body area network. So everywhere you have now sensors. And so idea is that all these, and the sensors are low power devices. So conceptually, it should be possible to energize them using this, what we call the this harvesting devices, provided that they are compact and they can be integrated with the thing. Now, before the history, this everyone knows that it started, even in the 20th century, that you have the Tesla demonstrated that you can transfer power. So that's the basis. That, it's a wireless power transmission, but that is the application of this. So that is something you know already. Now, very interesting part. There are twins: wireless power transfer, RF harvesting. I will mainly talk on this part, RF harvesting, but conceptually, the same concept can be used for wireless power transfer. I should say that as of now, conventionally, this is being done using inductive coils. So there is a challenge that can you use them to, for example, energize very large network. We have now everywhere electric vehicles. And it's coming up, it will come up more in future. But you also know that to charge, you have to go to some station. Now imagine a scenario that you move a vehicle on the road, the charging station, and while you are moving, it is getting charged. So without any physical wires into picture. And that is something what is in the sales for wireless power transfer. So what you have? So in RF harvesting, you have actually the antenna. Antenna will receive the power. It could be, from Wi-Fi, from cell tower. It is some matching for impedance, and then you have rectifier will convert to DC, and then finally you have the DC. So that means here you start from energy in the ambient. However, for wireless power transfer, what you want? You want to transfer DC from one point to another without any wire medium. So the concept is that if you have, again, power amplifier, Professor Shastry is there, so you can use this high power efficient. Of course, the idea is that you should have efficient amplifier. So that like RF to DC efficiency is very high, so that you can convert basically almost all the DC into RF. Then you have antenna to sustain high power. And then you can transmit this high power RF power from the one antenna to the receiver. Imagine that this is something inbuilt in your electric vehicle. So basically you have an antenna, you pass by, and you basically receive RF from this thing, and then it converts into DC and it charges your battery. That's something that, how is it different from what we call the wireless power transfer. And that is a very commercial entity because, electric vehicle will be used everywhere. The challenge actually, if you see the challenge is less in wireless power as compared to RF harvesting. The reason being that as of today, for RF harvesting, the energy which you have is very low. If you use a mobile phone and if you see the power, it may be minus 80, minus 90 dBm, very, very small. So the challenge is, and most of the rectifiers, they will not get switched on at this much low power. The challenge for RF harvesting is that can we try to work at very low RF power? On the contrary, if you see wireless power transfer, you have high power. You already, because you have converted, DC into RF. This is in your hand. It's just like you have to transmit this over a distance. Of course, you have high power in the free space. You have to be careful about the safety concern. But this is really in near field. So and because it's a near field, high power, so that's not a big issue. The only issue is that how much energy is being wasted and how much energy is actually being, because you have two-fold transfer, DC to RF and RF to DC, including the matching network. So you have to have a system which can have such a high efficiency that if you convert from DC to RF, RF to DC, and then if not 90% power is being transmitted. But that's not the practicality. Concept-wise, everything is fine. We don't see any bottleneck as far as the concept is concerned. So, and if you compare, so it's a shorter distance, it's a near field, and you have a transmitter, and you need high efficiency. But this is something like and this is not difficult, because if you look at the literature, efficiency of these rectifiers, they get reduced when you have very low RF power incident on the diodes or rectifiers circuits. So if you already have high power, which is being beamed into your RF, rectifier circuits, you are one step ahead. And that means that is something that can actually be utilized for this application. So that's the background. That means conceptually, RF harvesting, wireless power transfer, they are the same, but something, different is in the way you want to have the transfer of power. This is something typical, we call them rectenna, because this is rectifier plus antenna. That's a typical or conventional RF harvesting. So you can see there, the first thing is what we call antenna, which is used to receive power from ambient. It could be, from any source, from the Wi-Fi, from tower, from cell tower, anywhere. And then, before you convert them into DC, you need to match the impedance. Otherwise, most of the power will come back and it will go back to the source. So, it's also equally important that how can you have good matching network so that
most of the power which is being received from the antenna goes to the rectifier, and then again, so basically it's nothing but diode. But again, there are shortcut diode and other diode configurations. If you see in details, idea is that you would like the diode to operate at very low DC and still try to give the power. That's why you need special diode. Otherwise, and you have dual topology or other things. So this is something you can always see in the literature. But the idea is simple, and you have to cover that because you want to block DC and come into the rectifier. So, and then at the end you have a system where you can whether you want to charge a device or you want to store it. So that's typically what we call a network which can be used for this kind of configuration. So there you need very high power, as I mentioned earlier. Antenna, you need high gain because at the end you have very low power. If you don't have high gain, you cannot actually receive the power. And at this frequency, again, polarization is important because usually we say should have high gain. But the challenge here is if you use high gain antenna for wireless power transfer, you can receive energy only from one direction because most of the time you would like to have a topology where you can get energy from different directions because you don't know from where power is coming. That's again a challenge, that how you can trade off between the gain and the power which can be received by your antenna, or what you call omnidirectional antenna, if it is possible. Matching network, again, as I mentioned earlier, so you should match with the frequency. And this, again, it's not straightforward if you try to design, but it is something like if you have expertise in the RF, you can do that. It's not something, impossible. And finally, the rectifier is a very important part. We want to convert RF into DC. So you can have single stage or multi-stage. And sensitivity is an issue which basically means that you want to see that how a small RF power can be, for example, if you have let's say minus 80 dBm of input RF power, can it be converted into DC? That can happen only if you have high system sensitivity, and that's something which is actually important. And yeah, again, you want to have store or you want to have the output voltage. So with this, I just come to, I will not give a detail, but I just tell what we have been doing for the last few years. So this is the first thing which we design, this is a simple dual band antenna. Again, why we have wanted to have dual band or multi-band? Because at the end, you have many sources. If you have a single band antenna, you can only receive energy at one frequency. It appears that if you have multi-band system, at the same time, for example, you can get energy from Wi-Fi, you can get energy from cell tower, Wi-Fi at 2.45, Wi-Fi at 5.5, cell tower is just a 1.8 gigahertz, 5G at 3.5. So if you can system which works in all the bands, so you can basically, in principle, try to get energy from all of them, combine them, and convert into DC. And that's why, we try to see it is multi-band. So this is like a dual band system which you design. And you can see there that you have multiple signals. So this is the frequency you can see there. And you have again, array is 2 by 2, 2 by 1, but actually it could be many. Just like to show the demo, the student, what we did. So just to show that if you have gain. So as I mentioned, it's better to have, array rather than single antenna, because in this case, still you can try to get energy from many directions. If single antenna, the challenge will be that it is only in one direction, and that's something that might not work properly. So this is like, the band here is 1.5 to 2.65. And this is again, this is actually from this frequency. But the problem is it possible to have matching network, antenna, and the rectifier at the same frequency? And the answer is yes, but it's difficult. It's a challenge. So you always try to find a trade-off. That can we try to, for example, find out that, okay, if you have multi-band antenna, at least rectifier works at 2 bands. Because, matching and both rectifier, they both at the same wide band is not very easy. So this is something like, you can see the antenna pattern, and this is like how you can do the measurement. It's very straightforward. For example, you say you have the transmitting horn antenna, receiving antenna. This is something that we have designed.
And this is a typical far field, and we can see, for example, how much energy is being received by the antenna. This is just normal antenna stuff. And rectifier. Rectifier is something, it also has inbuilt matching unit, as you can see there. As I mentioned, matching is again difficult for multi-band or dual band because in this case, for example, you see there are a number of transmission lines. They are being used so that you can match at least two, if not all the frequency components. Now, if you have matching, you have either you use lump network like Shastry or something, or use what we call the distributed. If you use lump network, the problem is that they work over wideband, but they have losses. You already have low loss coming from the antenna. If you now introduce more losses, you don't get anything into DC. That's why we always try to use something which is distributed for matching network, so that especially low loss, so that at least if the energy is being received at the what we call antenna, it is being converted into DC. So that's something actually what we can do. You can see there that this is actually a dual band, works at these two frequencies, and finally you combine both. That's again actually ideally it would be on one board. That's not possible in the beginning, so it's also fine if you can, for example, use antenna separately, rectifier separately, then you can connect to the SMA cable. That also is fine. This is something what we adopted in this particular case. So this is a rectifier network, so you can see there, again in rectifier, what's the challenge? You can see there that if your input power is going low, efficiency is coming low. And this is actually RF to DC efficiency, and that's the main challenge. That it is good if you can work at high power, but practically in the ambient power is low, and so if you really want to make use of them, you have to be careful that can we achieve such a, practically few volts required for this using this system, and answer is yeah, it's not very easy. So again, this is just to show that, for example, like this I was showing. So this is a typical diagram in the chamber where you can, for example, put this rectifying circuit, connect with the first. What you do, the steps are that first you use antenna, you use a spectrum analyzer and see how much RF is received. Take the spectrum analyzer out, put your rectifier, and then see how much is being received. And in this case, very simple example to show that if you have a mobile phone near this is your antenna, rectifier, and this is like a load here is your LED. So if you use this, if you switch on this, for example, mobile phone, which is Wi-Fi is committing, this is received by the antenna, and this antenna is converted into DC, and this is enough to light up this LED bulb. Just a very simple example, a very good example I would say, but the idea is that it's just concept to show that they can be used to energize low power devices, but it's being available in the ambient. That's something actually what you can try. And there also you can see that both at 1.8 and 2.45 gigahertz, this 1.25 is Wi-Fi, this is your cellular mobile communication. In both the cases, if you come very low power, low efficiency, that's something actually not a good thing which you would like to achieve. Now, after this, we try to use triple band antenna, and that to differential antenna. That's something actually very good concept. It was very, very high citation. The concept is simple, that first of all, because the major challenge in the RF harvesting is that you have noise, you have very low signal. So it appears that if you have differential topology, so at least you can eliminate, minimize, if not eliminate, the common noise, and then you can afford to work even at low SNR level. And so that's the advantage of what we call the differential antenna. And then triple band means simultaneously you can, for example, work you can get energy from 3 different sources like cell tower, Wi-Fi, FM, and so on. So it's just like, it can give for any band. But the idea was just to show that if you have 2-in-1 differential
to work practically with low noise, minimize the common mode noise, and triple band means you can now, or you have the possibility, you have the luxury of getting energy from different sources put together. And that's something actually what we have tried to achieve in this. So this was, 2.65, 2.5. Of course, the bands, students when they try it, they get shifted, but that was the concept which we wanted to have a 2.45, but this went to 2.55, but that was just because they couldn't control the parameters. But the concept is that you can use this for, and here you can see the antenna. You have also the reflector so that you can increase the gain. And and of course, because differential thing, so you have to be careful about the measurement of matching. This what you can use this formula. So now you can see there that the pattern at 3 frequencies, they are able to be fine. That means you have enough what we call the gain at all the bands, and especially theta grows 0 pattern. If you see there, so this is actually. So you can see here in this figure that for the normal thing, all the 3 bands you are able to get energy with high gain, and that is enough to at least get some energy at all the 3 operating frequency bands. Rectifier, again, because you have a differential antenna, you also need a differential rectifier. And that's again not straightforward. So what you can do here, what you see here, that this is a differential rectifier topology. Practically, it is difficult to measure. That's why we have put in 2 different sites, port 1 and port 2, so that they can be connected to the antenna in the differential mode. And then finally, you can see there that here you will take the output DC from here, and this is something like details, for example, how to connect the and all they can get in the paper. But that's like we again try to use mostly IDC rather than the RAM component, so that like we minimize the reliability. I mean you have improved reliability and also minimize the what we call losses. And this is something the final measurement. So as you can see there, this is put up in the chamber, and the spectrum analyzer put there to see how much power can be received. So this is a typical measurement which you need for the output power and also for the DC. In the same way, now say can we have wideband? So this is sort of again scaling up the things. Nothing very. So you have again you have different antenna. You can see there are different directors to have this multiple band, and this is a range which you can get. And this is and because it's a differential thing, so you need again what we call the hybrid coupler to because anywhere if you have to measure differential thing, either you use 2 ports or use hybrid coupler, which one of 2 are in pi/2 phase, so that like they can correspond to that particular signal. So after you do this, you can actually see. So this is again, the measurement of the antenna, actual thing. So this is just to show that how you put. So you had using a normal horn, and you can read actually the voltage also. So this is a 14.8 millivolt, what you can read here. So this is so efficiency is again, if you see there, what you can see that even at low power, you are able to get something which is not very bad. But we would still like to have higher efficiency. So that in all the application for RF harvesting, for low power, the challenge is that we are not having enough RF to DC efficiency, and that's why they are not yet commercialized. But of course, we have to work on this. Finally, on this, we wanted to have flexible antenna because also so that like you can fold it. Because imagine that rather than having a very rigid thing, if suppose you have some system where you can fold and you can get energy from various directions. And the idea was that if you can fold, you can get energy from multiple directions without moving your antenna manually. And also without using any diode or any sort of complicated active circuitry. So that was the main concept there. So in this case, like you can see there, so antenna was special. So this is like the unit cell of the antenna. So there are 2 loops in together, and this is like a magnetic AMC, which is put up again to work on the gain. And what is the main thing here that we have used 4 different antenna systems. What it means is that rather than using one antenna and one rectifier, we have a system as if there are 4 of these, antennas which has antenna plus rectifier. They all work simultaneously. They are in different directions. So at the end, all the energy from different directions can be combined to show that if you have one at a time, others are not operational, the beam is moving. That means if you actually, in principle, have all 4 switched on, then you can actually expect to get energy from all directions. That's something actually what it shows, technical structure. And now, let's say if you have 2 different, in this, look at this, there are 2 sources, one horn, one patch, 2 different frequencies. So at the end, this is connected to what we call the spectrum analyzer. So you are able to, in this case, a simple experiment to show that you are able to actually, and this is again the DC voltage with the rectifier. So idea is that to show that if you have multiple sources working at the same time, in principle you should be able to, or you are able to convert them into usable DC, and the DC is augmented due to energy from different directions with the help of the different antennas. That was the aim, what we wanted to show here. So this is the actual diagram. Now, this was a conventional system which is being used most of the time, antenna and a rectifier. Now slowly, people are trying to use FSS, which is called frequency selective surface. You can also call metamaterial, but they are usually FSS. Frequency selective surface, they are like the filters. So they are being used in place of antennas to receive energy from the ambient. What's the motivation? So if you see, concept is the same. So you still have, rectifier, you still have what we call the DC and all matching circuit. But rather than antenna, you have now FSS, frequency selective surface. The idea is, as I mentioned earlier, for antenna, it makes sense to have arrays rather than single antenna. Now, if you see the complexity, it is much easier to have FSS array as compared to the antenna array because they all can be made in one go. Here, you also have more flexibility. For example, in future, if you want, you can also try to use different sizes, different thing, everything made in one go. That's the reason why people are now trying to use FSS rather than the antenna for what we call this kind of application. And this is called FSS-based harvester. So that means they are, and if you see the particular thing, so there you can have adaptive design because you can have reconfigurability, because the whole media surface comes from this, that you can change the unit size if you go from one point to another. The whole thing can be applied also in this particular case. You can, suppress some frequencies if you want, because, that's, something very interesting. Because imagine that you have designed a circuit and you want to have a notch at some frequency. That's something, you can always, do using this particular system. You can scale up and you can have, more versatile design because you can have different unit cells, different shape, different size, made on the same surface, and then that can be used to match with the rectifier to garner DC or, from the ambient. That's something actually what is being tried. This was tried in just some other paper which was done, few years ago. But there they have tried to do that. If you have FSS with some, scaling kind of thing, you can try to make on the same surface. You can scale up or scale down by making sort of some channel together, and that is working. And they say that if you make the channeling traces, you can actually be more, it can give you more flexibility. That's something what they are saying. And conceptually, they are saying that you can receive almost all the energy from the ambient. That's of course the wishful thinking, but that's something like what we envisage. And that's something what they have proposed. But the idea is that this is working. So you can have FSS of the rectifier, it can work at some frequency. And this is again like the input impedance circle because you have to match with the FSS. And this is
like the two frequency radiation means that how much power is being converted received by the antenna and how much is converted into DC. Now we have done similar work. So we just started this. So if you have this again, MTech student who started working on this. So it was made up by this simple FS array. And the one problem is that, for example, if you want to match this, they are not 50 ohm, so you have to put some extra matching circuit in between. So this is why you see here some sort of FSM in the connector to match this thing with the rectifier. But in principle, yes, we are able to check this first, the only FSS, and then we try to measure RF power in the ambient. And finally, rectifier was made on the same what we call same frequency, and there was one assembly connector so that like you can match the impedance of the FSS with the rectifier. And finally, you can see there that this is the rectifier efficiency which was received. Yeah, and this is something where we combine. So again, the same testing. So you have the horn here to transmit, and you have here what we call our structure which we have made. So other antenna, you have FSS there, and we convert it. You transform, connect this to a spectrum analyzer, and see how much power is being received. And you can compare that the power which is being received by the spectrum analyzer, how much different it is from the power which is being given by the transmitter if you apply this equation. So that you can do the calculation, you can check that how much loss is in the power and how much efficiency this FSS is giving. So this is again like what you have to see here. As I mentioned earlier, that you have to match impedance. You have to apply some impedance transformer also before you try to connect this FSS to a rectifier. Recently, we have tried to also get some review article on FSS-based structure, and using one thing here. What you can see that we have tried to check if you have say 20 by 20 FSS cells. Is it that all the cells are getting same RF energy, or is it different? And for this to happen, what we did is that we tried to, for example, measure rectifier at different, for example, you see here all these cells. So there this is one in the corner, the center, and this corner. So we tried to measure power, and you can see this the profile. And you can see there that this one at the center gives maximum power, on the edge gives less power, provided that it is put up in front of the horn antenna. But that's also obvious, because antenna which is direct in the plane of the antenna get maximum energy, other at the edges they get less energy. So I mean, what our idea was that we tried to do bit by bit to see whether that works conceptually. And what we found that yes, in principle it's working. We have to work on a number of things like the matching part, the comparison, how to integrate, and finally, my final thing: can we make system which is hybrid? For example, can we combine solar with the RF? What's the advantage? As I mentioned earlier, the major challenge with the RF harvesting is that they are not able to work at very low RF power, and this is very low. So if you can have one, let's say, solar cell put up with the your what we call antenna system at the input of the rectifier. So what happened that diode knee voltage is very, very low. So if you can give the initial boost by putting diode into that on condition, then one can see that both solar and RF can be combined. And by solar, even you can also have piezoelectric transducers, temperature sensor. And there are so many sensors are in the market. So this is again, if you are a student, this is a good area to pursue research. That can we have a system for energy what we call harvesting, where multiple sources, including RF, can be put up in place, and they all are green energy. So, it goes also in the direction of energy efficient system. Because at the end, you are able to energize your devices at a very low, without putting any extra DC or any extra source. That's something actually what one should try to see for the future thing. And lastly, because they are the student work, so Sandhya, she did here, now she's working is in Germany. She is still doing PhD. So I mean, like, the good part is, so like, after she did PhD, she worked for postdoc and then she got offer in Germany, which is, so that means that people are now actually also working in the industry after pursuing PhD. That was something not seen in the past. So that's also one should try to see that people who are in the engineering field, they pursue PhD, they should also go to industry, so that like even startup, as I was saying, so that like they can actually, use the technology, because concept-wise they got expertise. If they can use it, to really make it convertible thing, that's beautiful. And I think that from that way, I will say, well, Shastry and group, they are doing very good work, wonderful work, that we should try to put anyone on a single platform so that, we can put it forward. Thank you very much. If there are any questions, I would like to put up. Any questions from anyone? Yes, sir.
Very interesting talk. So the question I have is, I'm Sanjay Nayak from RFIC Solutions.
Yes.
Question is, it looks like at least for low power devices, it should be possible to have this wireless power transfer. Let's say for Bluetooth or watch or for, based on this work, it seems to be, it should be possible for most applications where the power is very low.
Exactly. If you have microwatt or milliwatt, it is possible.
Power transfer directly without any batteries and all that.
Exactly, yeah. That's the concept. Yeah.
I would like to maybe talk to you privately and see.
Yeah.
We have a lot of good IC technology. And with IC technology and a lot of smart antennas and even low cost, it could be possible to make a system that really provides power for low power devices,
Yes, yeah.
So very interesting talk. Thank you. Is that possible? What do you think?
Yeah, that's what I mean, because, I don't see anything, only thing you have to just realize is, the modality. Otherwise, conceptually it is fine. So I don't see any challenge, yeah.
So we are making a product that really is a very complicated RF chip, but it's really does energy harvesting from minus 10 dBm. It's a CMOS chip. It just basically wakes up the system, and it's done with a US company. So there is a lot of power management and complex transmit receive systems. So that's a very sophisticated system that is probably good for US. I'm looking for products that are really targeted for India.
Yeah,
cost, earlier talk you gave, that you need to have for India, cost has to be like 10 times lower.
Yes.
Whatever is $10 in US, India has to be $1. And even that, so something like that, I think is possible. The chip we are doing is targeted for US.
Yeah.
That's a very sophisticated chip. Making it $1 chip is not possible.
Yeah.
But US can afford $10 chips or $5 chips. For India, I'm looking at ideas you have or what you showed here. Maybe we can talk to you separately.
Yeah, because so it is sort of hybrid. You just need antenna and input diode put together. So, so that is sort of you don't need very hi-fi components. Yeah, that's true.
So I think it's possible to make products for India based on work you have done and work we have done.
Yeah,
so
sure.
Maybe we should talk separately. Very interesting talk.
Yeah, sure. Anything else?
Excuse me, sir.
Yes.
This is Ravi Kumar from Dayanand Sagar College of Engineering.
Yes.
I am actually pursuing PhD on this area itself. So the RF energy harvesting, whatever we are doing, okay, the power is coming from, like, say, Wi-Fi, TV towers, mobile towers. Okay, is it legally permitted to use that power?
In that?
Legally, is it permitted? Do we need to take permission from the...
That boss can tell. I don't think there's some legal aspect because, you are not tapping information. You are trying to convert into DC. And we have not reached that stage yet, okay? When we reach that stage, we say, we are trying to develop technology. Now, once we reach that stage, we can say.
No, for the research purpose, I think in the starting it is okay. No, we are using the RF energy.
Yes.
No, let's say I have a tower next to my home, okay. Then I deploy like hundreds, let's say 100 such antennas.
Yeah.
And then is it not going to block the power that is going to be?
Yeah, I mean, that's something is a concern, but we have not reached the stage. No, that has become, everyone has a house, then probably, yeah, something. As of now, still people are trying to see whether you can still do it or not.
Okay.
But if it becomes very commercial, everyone uses it, then yes, somewhere you have to give a thought that whether it is allowed, because then, but as of now, power is just going waste.
Yes.
The fees
As
will
of
be
now-
more than what you are using.
Yeah,
Yes.
yeah, yeah.
Yes, sir.
No, I was interested in the hybrid approach.
Yes.
Now, why would one do that? Because the solar people say, why do we need RF? There's plenty of solar energy.
Yeah.
Why should I combine RF energy harvesting with solar energy?
Yes, yes. Because, solar energy has some, because for example, if you are working in some region where there is no solar energy, you cannot work. You cannot work in night. On the other hand, RF energy will work all the time. So if you can have, for example, some sort of charger which can charge, say batteries using both solar and RF, so that's something RF can get going on, and solar can switch off.
That makes sense when they... Yeah.
Yes.
Has anybody measured and plotted the energy density, RF energy density in different locations? Okay.
Yes, this is something actually also very, very interesting aspect, because some people, what they are trying, that if you really want to develop a system, you should try to cater to a particular area, because they can't be the same. For example, let's say I am at Kanpur. What I should do, I should try to measure this, let's say all around the cells, and then say, okay, how I can try to develop a system which works in this region. That's a good point. That's true.
If you have in metropolitan areas,
yes,
there is a lot of RF energy.
Yes, yes.
If you go to villages, yes.
Yeah. विलेज में नहीं, बट वहाँ पे सेल टावर गांव में तो हर जगह पे सेल टावर वो लगा हैं, अपने सेल टावर उसको आप वहाँ यूज करो आप, या समथिंग ना, सेल टावर दे देंगे.
So is there anybody commercially trying to do energy harvesting, not power transfer? Power transfer, I know many.
Yes, yeah. I am not aware of because that main challenge is like this, how to work at low power level.
What Dr. Moghe was talking about was probably for power transfer, wireless power transfer. Long distance, that is far field.
Okay, power transfer, yes.
Power transfer.
Yeah. Power transfer is not that much difficult, because you have power, you just have to transfer. But here you don't have power even. So that's sort of more challenging, So, yeah.
It's very, very, very interesting.
Thank you.
Particularly, I'm interested in the hybrid approach.
Yes, yeah.
Are you doing something on the hybrid?
Yeah, I mean, one student would try to do some measurement using solar cell or something, but it's still, has not been published, so it's still going on, But we are doing some work, But not yet, come up in open,
Thank you.
Thank you. Yes.
Hi, sir. Then regarding the sensors use very less power.
Yes.
But then you also need the microcontrollers to be attached with the sensors.
Yeah.
So then the microcontrollers with the sensors, they are going to consume more power. Is the energy harvesting system, can it be able to power that?
Yeah, I mean, that's, always a problem, because even for CMOS, there are times say, can we reduce the power consumption? So we go with this thing that, when we come to this level, the power required for the whole system will be less, which can be, used, or which can be dictated by this RF harvesting. This is something what is our envision. Yeah.
Similar things we did in cochlear implant. One thing what we did was long back, we did a cochlear implant chip, but there is not a harvesting. The problem is, can you power transmit from outside source to inside without any contact? For example, the deaf people, cochlear implant chip, they put it inside the head. So they don't have a ear. Okay, ear means cochlea is not there properly working. What they do is, inside a chip, it is connected to the brain where the sensing happens. Then what happens is, but the problem here is, RF power has to be given to it, and signal processing has to be done inside, so that the brain understands. Okay. So for that, complex signal processing has to be done, but
Same thing with like pacemaker also. Pacemaker also we can do.
Yeah, exactly. Yeah, yeah, sure. Yeah.
So, actually,
Yes. Yeah, sure. Yeah, yeah. Yeah, yeah, understood. Yeah, yeah, yeah. Yes. Yeah. Exactly. Yeah, sure.
our colleague, Dr. Rosalind, is working on wirelessly powering a pacemaker.
Yes, yes, yeah. Very important part, yeah.
Yeah, similar to that.
Yeah.
So there was also one person who was interested in application to agriculture. So I said that nowadays they are using the concept of IoT.
Yes, yes.
The
Yes.
sensors are in the field.
Exactly,
They
yeah.
can be powered, low power sensors.
Yes, 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 yeah.
Using RF energy harvesting.
Exactly, yeah.
And so that's one other
Yes.
application.
Yes, yes, exactly, yeah. Sure.
Okay, it was a very thought-provoking.
Thank you.
Thank you.
Thank you very much. Thanks, sir.
Thank you, sir.
Thank you, Dr. Jalil, for the insightful presentation. Your contributions today have been truly inspiring, and we are grateful for the opportunity to benefit from your extensive experience and innovation ideas. As a token of appreciation, I would request Dr. Prestige Shastry to honor Dr. Jalil Akhtar.
Oh, okay. I have it here.
I'll just introduce her. then-
Okay.
So now we have a recorded session with Dr. Paul Traxler. So it's now my pleasure to call upon Dr. Prestige Shastry to introduce our next speaker, Dr. Paul Traxler.
Thank you, Dr. Rosalind. Dr. Paul Draxler is Iridium's Vice President of Technology with over 30 years of experience in hardware design and R&D efforts. Most of his past experience was at Qualcomm. Paul's expertise is in advanced power amplifier, transmitter, and transceiver designs, and the associated digital signal processing to create the desired performance. He has a BSEE and MSEE degrees from University of Wisconsin-Madison. That's where I met him. We had the same mentor, and I was a postdoc, and he was a student there, so we worked in the same group. He has a PhD degree from University of California, San Diego. He is a senior member of IEEE and has authored more than 40 papers and 20 US and international patents. So currently, Paul Draxler happens to be vacationing in Alaska today, as of today. So we initially tried very hard to convince him that he can speak to us from the ship. But then we realized the communication, through satellite, etc., depending on the weather, could be bad. And so we pre-recorded his presentation, and so we are going to play it. Thank you.
Thank you for the kind introduction, and good afternoon. The motivation for this talk is to highlight how power amplifiers distort signals, causing reduction in the throughput for the communication signals that we send out, and how the additional nonlinearities that are caused by that compression and distortion on the signal can affect the performance. And by improving the efficiency of the system, we actually start causing more compression, but we can actually correct some of that with digital pre-distortion and ultimately increase the throughput, resulting in a high throughput as well as a high efficiency. We'll also talk about in the presentation today two techniques that are used to change the rules on the transmitter to make it more efficient and allow that high throughput by doing the digital correction to the signals. And that's by using envelope tracking and direct polar, which shift the percentage of the time that the device is actually running rail to rail. Normally, a power amplifier is only running rail to rail at the peak power levels, and most of the time you have this excess overhead. But by continually modulating the supply and running the final stage in more of a switch mode, that creates a higher level of efficiency, albeit with some distortion. So we will use digital pre-distortion to compensate for that distortion, resulting in a high fidelity output. Now you'll notice I didn't say a linear output. It's a very nonlinear process, but we wind up calibrating out those nonlinearities and that distortion such that we do ultimately get a high fidelity output, which results in a clean spectral content. Rather than getting the spectral regrowth, it gets canceled and we wind up with meeting the ACLR targets and also high EVM. And we do this achieving a high energy efficiency, low power dissipation, and reduced power consumption. The outline of the talk today, I'll start out with digital pre-distortion basics and how one can look at a large power amplifier, add in a digital pre-distortion block in the pre-processing before the DAC, and show how that you wind up with a reduced power consumption in the overall system. There's a number of steps to this calculation, and I'll walk through all of that. I'll then highlight how to quantify the limits of memory modeling and what you can achieve by doing memory modeling. Although I will warn the audience at this point, if you have to resort to memory models, make sure it's a good PA to start with. Memory modeling can correct for minor memory effects, but if you have too much memory effect, it's better to go back to the original design of the PA and make sure that the memory isn't excessive and due to some issue in the design that can be corrected for very easily, such as a bias supply or a supply voltage line. And then next I'll highlight a technique that's referred to as a doubly orthogonal matching pursuit technique, or DOMP. It's a very efficient way to implement DPD that only selects the key regressors or key terms that are affecting the distortion. And it's a sparse signal processing technique, which some would argue is a machine learning technique, but it's a very efficient way to extract out a inverse model that is ultimately very efficient to implement in a closed loop system. I'll then touch on some of the things that can happen with massive MIMO systems and the signal processing that would go with that. And then finally, I'll go over envelope tracking systems and direct puller systems in the way that the company I'm working with today, Iridium, is rolling out small cell base stations. And then finally, conclusions. So this is an example of a high-powered standard Class B PA, we'll say. And most PAs that are deployed in communication systems today will have a high peak-to-average ratio signal in it. For argumentation's sake today, I'll say we'll use a 3 dB PAPR waveform, which is pretty low for most systems today, but it gives me a clean number to work with. Let's say this power amplifier has a 40-watt peak power, and we have a, when we operate this PA, we want to have a clean spectral content. We want the spectral regrowth to be below a certain level, and the EVM below a certain level. And for argument's sake, I'll say that we have to back off an additional 3 dB to have the spectral regrowth within spec and the EVM within spec. So that would result in a output power with a modulated signal of 10 watts. 3 dB backed off for the linearity performance targets, and another 3 dB for the PAPR. So that would be a 10-watt PA in order to pass the linearity specifications for a QPSK signal. So if we have this PA and we've backed off 6 dB total, and this is a Class B PA, we can then estimate from the basic power amplifier compression or efficiency curves what that efficiency would be. Now, I'll come to that in a couple slides. If we just shift the saturated output power, that would be, let's change this to a pointer. So let's say this saturated power here, I was able to bring it down to something lower. I can actually do that by shifting the supply voltage at the output. So if I drop the supply voltage, the supply voltage squared corresponds to the PO sat up here at this point. So I can back off the supply voltage to create a smaller PA, which will give me a smaller PA to work with. This lower power PA, which has a lower PO sat, but I can add in a DPD block. So now if I'm trying to hit that same power level of 10 dB, or of 10 watts, I can have the DPD block and PA act as together as a gain block with a limiting capability. My peaks will be up in the saturated range, and we'll do the crest enhancement to counteract this compression characteristic. In that way, the power amplifier itself has now reduced its power consumption, but I'm still hitting the 10 watts of peak output power, and my average power is 3 dB backed off from that peak, the peaks that I'm exercising with this waveform shaping across the lineup. So my DPD block injects enough signal in here to counteract the compression characteristics here. So this is doing crest enhancement, this is doing crest crest compression, and the result is ultimately here at the output, a nice linear, or I should say high fidelity output that matches what I have at the input to the DPD. And that way I can reach my linearity goals of this system. So how do I calculate, based on this discussion, how much power I have available to do the DPD block for that calculation, and what's my budget now based on this resizing of the final stage PA? Well, I can go and look at the Class B efficiency curves. If I had just the 3 dB PAPR waveform, I could be up here at 42% efficiency for the Class B PA. This is with the assumption that my peak CW efficiency is 60%. If I back off 3 dB, I'm at 42. But if you remember back 2 slides, the efficiency was not at the 3 dB backed off, but 6 dB backed off, because I wanted that same linearity performance at the output. Now, when I bring the VDD down, that essentially resets this compression, the efficiency curve for the red curve here. And this is now my 3 dB backed off point here, this red circle. And you can see I'm back up at 42% efficiency for the final stage. But that's 42% efficient with a 10 watt output power. And I'm using a 20 watt peak power for that particular trajectory. So I'm actually dissipating a lot less power than I was even in this case here. This is a 40 watt peak PA that I was backing off to 10 watts, where I was operating at a 10 watt average power. And I'm at 30% efficiency. And so this is a significant savings in power dissipation. So now I would have that power savings that I have between these 2 points of operation, this one down here and this one up here, is what my budget is for my pre-distortion block. When we get towards the end of the talk, and I talk about the doubly orthogonal matching pursuit technique, you can see that the calculations to perform the inverse model and inject that negating distortion, or that negating signal to counteract the distortion, is very, it can easily be performed in an FPGA or in digital circuitry, such that I stay within that budget, even on a device the size of a handset. So just to reiterate, the digital pre-distortion block is going to do, in a classic RFPA environment, it'll perform gain expansion to counteract the gain compression that the power amplifier sees. And this is primarily, we've been talking about memoryless models here, and we're going to be essentially inverting these lookup tables in the digitally before we put the signal out through the DAC. I refer to this point here as the pre-distorted input, which in essence has crest enhancement, and we will specify what that output power is out here and how we're operating the PA, such that we introduce just enough pre-distortion signal here to counteract what the distortion is out here. If you set up the lookup tables correctly, and I'm only exercising a small portion of the compression characteristics, not going fully into compression, correspondingly, you won't introduce as much crest enhancement in the digital pre-distortion block. So this chart, this block diagram is a little bit simplistic in that one of the other inputs to this pre-distortion block is the target output power and how far into compression you are. If I build this lookup table correctly here, I can change the output power out here by dialing how far into compression I am here, and this input pre-distorted waveform then has more or less crest enhancement to correspond to how far I'm pushing the RFPA into compression. So this is some mathematics to say what I just said. We're going to create a predistortion signal that is the gain of the digital predistortion times the input signal. So this is going to be this gain or this crest enhancement gain block. It'll vary with the input voltage level or signal level, and that would be this memoryless term here. Now we're not going to try to correct for any memory terms or any noise terms in this. I'll come back to these two terms in a future slide. So my memoryless model ultimately is going to be a gain term times this input signal on this side. So, and again, as I said in the previous slide, this combination of blocks winds up looking like a gain block until you hit saturation. And then when it saturates, you don't drive it any harder and it doesn't try to push further out. If I try to achieve a power level above that saturated power level, in essence, you create an infinite peak to average ratio signal, and that's just not a good thing to do to your DAC or to your system. So you want to limit how far this crest enhancement goes and limit the range of the input signals so that it doesn't try to go beyond the saturated level. And so the way I depict that in this slide is that if you're above saturation, you set it to VOSat. That's the saturated voltage out here. And if you're below that saturated voltage, you have gain times the original input signal here. And I'll come back to the memory term and the noise term here in a next slide, or in a future slide. Now, the other thing I want to highlight here is the matrix equation that I'll often be using as we go through the process. If I'm modeling this as a polynomial, I can refer to this as the output, and I can use the input signal times a gain block, a gain level, A1, let's say, a squared term with an A2, a cubed term with an A3, and so on. And these would then be the A1, A2, and A3. So this is referred to as the measurement matrix, and the A's are the coefficients of the polynomial. Now it turns out, when we get to it in a moment, and you've probably heard of people refer to Volterra series models for memory models. In essence, what that is using a polynomial model for no delay on one axis. And then if I look at the linear term and create a FIR filter with a frequency response, to create a frequency response, that would be your classic equalizer, classic FIR filter. It turns out a Volterra series essentially starts with those two axes, but then fills in the whole matrix of a delayed term and multiple delays and various delay factors within that entire matrix space. If you try to do a full Volterra model, you're going to have too many coefficients to extract. It's going to take way too long to identify the model, and it may not even come to a solution even with a good least square solver because of the overspecification of parameters. So we'll talk about a better way to address memory models and that extraction in some future slides here. So what happens when we do the memoryless modeling is we start out with a compression characteristic that looks like this with a modulated signal. In this case, we've used a vector signal analyzer to pull out the I and Q samples at the output of the PA, and we create this light blue model going down the middle of the dark blue dots as the expected value of the gain throughout the trajectory. We use that to create our inverse model, and ultimately we want to create a response that follows the red dash line down the middle. When we perform the lookup table for the memoryless model, the memoryless compression characteristic, and then we look at the gain with the DPD, the gain after we've put the DPD block in, so we have DPD plus the PA. If you do it all right, you'll have the sample points with about the same scatter about the compression curve here, but now it's across the x equals y line here. And again, this is normalized V in and normalized V out. So when I normalize both of these vectors to a maximum of 1, you wind up going straight across this one-to-one slope across the performance space. So again, here we have our equation in a matrix form. This is the sample or continuous time form. And on the left plot here, we see our power amplifier with its performance, its compression characteristics, which include a memoryless model, a memory model, and a noise characteristic. So no correction has this performance. And when we add in a digital predistortion block, we now have corrected the memoryless term that was here and now have just gain times the input signal that give us the output signal. And everything snaps to the diagonal. But we now still have all of this splatter along the diagonal line. And when we perform another technique referred to as memory mitigation, which eliminates the memory terms about the sequence. These were originally created in a circular sequence that's repeating over and over again. And so I used the memoryless model to adjust terms that snap the individual elements down to the target output. And what's left after I perform that ultimate memory mitigation technique is just the random variation that's left in the measurement system. And these are effectively memory terms that are not correctable. They're either spurs or some other noise effect that's not repeatable, and I can't correct for it. And so this is the limit of what memory modeling could do. It's always good to know what the asymptotic performance of a technique that you're applying, what those limits are. If you start to approach those limits, you know it's time to stop. If you're only going to gain a fraction of a percentage points in EVM, it doesn't make sense to double the effort to try to get just a fraction of a percent better. And so knowing these limits actually is very helpful in working through the amount of effort you should put in to do the correction and compensation for these distortion effects. So this is a memory polynomial, and what you'll notice is it's a polynomial in the U parameters here, but then there's also a delay for both terms or both entries here. Quite often this will be an odd order only for the polynomial order n, but there are times that evens will also be included. Arguably, the odd order terms are the ones that land in the zone around the carrier, and evens are going to be at baseband or at the second harmonic. But it turns out in some cases, the even order actually does create a better model. And so it's been known that even and odd order are used in the zone 1 correction model. It's kind of a thing that you need to try out and see what works best for your system. But you'll notice the double summation here. A full memory polynomial will have memory terms that go generally from a negative memory to a positive memory. Most equations only show from 0 up, but I'll often have values on both sides of 0 because we do a time alignment of the input and output signal so that we have a clear gain term. And by doing that, there's often what looks like a non-causal term at m equals -1. So generally speaking, you have a range of memory that goes both directions from 0, and then also a polynomial order that would be n. And this is the continuous time version of it. Essentially, you'll create a vector for the output, y, and that is generated here in the sample domain for all of these y terms here. And then you'll have each column in the measurement matrix a different pair of indices here for m and n for the u values. It's all the data that was collected for the input here, and the a's are over here in this column vector here, in this vector. And in this way, we can do a least squares extraction to extract out the coefficients for a. This is a generalized memory polynomial which has 2 memory terms referred to as k and m that are here. So you have different delays for the higher order polynomial entries and for the single order complex value here. Typically, you'll look at u as being in the complex baseband form. 2 of the other models that are often used, I've published something on the dynamic DDR with Anding Zhu in an open loop case, and also a piecewise DDR for envelope tracking. And then Anding has since published a DVR, decomposed vector rotation algorithm. It's a little bit more complex, but it has some advantages for certain types of transmitters, certain types of PAs. Generally speaking, I've been able to do pretty well with the memory polynomial and generalized memory polynomial. If needed, I'll go to the DDR, but I haven't seen too many cases where I've had to go to a DVR technology or technique. One of the interesting things about these equations, you'll notice all of the summations go from 1 or 0 up to some higher value. This creates a very full slice for the model. And it's not all the terms are contributing equally. It turns out that this technique that Juan Becerra has published, essentially you identify triplets or quadruplets depending on how many summations are in the Volterra slice that you're looking at, and it will identify which triplets or quadruplets are most effective in the nonlinear modeling and in the inverse modeling. So when you start out with your measurement matrix with each of its columns, it will say, okay, this particular column has the best correlation and give you a value for that coefficient. But then it'll perform a Gram-Schmidt orthogonalization that then ranks what's left and identifies what's the next term that will satisfy do the best at satisfying the equation in the next iteration. And so you pull that one out and identify its coefficient. So essentially you perform this iterative process of adding terms from the most impactful to the next one and the next one and the next one. So instead of extracting out a huge matrix, a huge set of coefficients first, and then pruning ones off that don't work, you start out by identifying which ones have the highest correlation, extract that coefficient, then look at where the next best correlation is, and then build it out one by one. And that's actually a much faster process to extract out a model. Quite often, I'll have a potential of hundreds of terms and wind up with only 30 or 40 terms total in the extraction that I ultimately wind up implementing in the FPGA. And in that way, you can create a much more efficient algorithm for a particular platform. This is a slide that I talk a little bit about massive MIMO. In this case, we have a 4x4 array, and each of the elements can have a different frequency and a different waveform in it. And quite often when you have an array like this, you'll get a little bit of coupling from one antenna over to the next. And when you get that, there's actually a load pull effect that occurs on the adjacent PAs from the signal that came out of the one transmitter. It turns out if you can sense this and get the feedback of what's happening here, you can actually take a little bit of the signal from one channel and feed it into the other with the right coefficients such that they cancel out here at the output. And so in this way you can reduce the antenna-to-antenna coupling that occurs in a massive MIMO environment. And again, this was some work done by Huda and Slimber Mesa and a few of their other colleagues up at the University of Waterloo and published at IMS in 2023. Now, shifting gears, if you remember back to the power amplifier class B curve, if I have a 6 dB peak to average ratio signal and I have to back off more to get achieve the linearity specs, I'm going to be down at a very low percentage for efficiency. And most transmit chains are not, they don't budget that kind of power for the final PA. And so one of the questions is, how do I bump up that efficiency and reduce the power dissipation? And one of the techniques that's been used quite often is envelope tracking. And this slide has a basic description of what envelope tracking does. Essentially, I have taken my single PA, my RF PA here, generally biased in a deep AB, maybe even class B. I have seen class F or F inverse down here and other switching mode type PAs. And I'm going to add a second amplifier to my system. This one's going to be at the envelope rate. So it'll be modulating the power supply. And so now on the system side back here, I'll extract out the envelope of the waveform, and then I've got my RF signal times the envelope here. And by getting the right kind of drain modulator on the supply side, I can modulate this power supply such that I'm operating rail to rail most of the time. And that's what both of these plots on the right are depicting. Here, instead of having a single rail up here, and we wind up dissipating a lot of the power between these minimum values and the peak, you can see that my supply is moving right with my envelope rate, right with my RF signal, and there's not much power dissipation. The way you can think about it as far as an efficiency over output power is, as I drop my VDD, my supply voltage, the peak efficiency backs off as each of these curves slide back on the slide over to the left on the plot. And the idea is to move this supply up and down this curve at the highest efficiency points, and in that way create a power optimized envelope tracking. And we'll operate at these points at the highest efficiency, and that way we're running rail to rail at that optimal point. So my RF is staying at that rail to rail operation throughout the majority of the power output probability distribution function. Now, when you do calculations for the efficiency of this system, to be fair, you have to not just look at the efficiency of the RF power amplifier, but you also have to look at the efficiency of the drain modulator. And so it's really the product of the efficiency of the RF amplifier and the efficiency of the drain modulator multiplied by one another. So if the RF PA is operating at 70% efficient and the supply modulator is working at 70% efficient, you'll have an overall system here that's operating 50% efficient. And that's that we've achieved that for WCDMA signals up in the 50-watt range. One of my publications from UCSD covers that kind of performance. One thing that makes this very nice is that the output target voltage, or in this case I'm looking at the input voltage, and the supply voltage have a one-to-one mapping. So you can solve these, the linearization problem on an envelope tracking PA as a simple lookup table. Just a simple 1D lookup table to map from VN to VD to Vout. It's all a simple one-to-one-to-one mapping. And this works very well for narrow bandwidths. And in this case, we've seen from 40 megahertz down, solvable with this kind of a system. Some of the publications I've done with MaxCentric, we allowed for a particular supply voltage a range of input voltages, which then would paint this whole surface down here on this side of the line to operate with and perform digital pre-distortion and compensate for the distortion on the signal. The slides that I show coming up are going to stay in this 1D lookup table regime for ultimate efficiency and repeatability and high linearity and high efficiency for small cells. This particular block diagram, this dynamic supply block diagram that's here, is used on a wide variety of systems with all kinds of different performance characteristics. A, of course, is a constant supply voltage across the whole operating range of the input. That's your classic Class AB or Class B or Class C for that matter. You hold a constant voltage across the whole operating range. That's a fixed supply case. Case B, the vertical line here, that's envelope elimination and restoration. And all the other curves in here are different flavors of envelope tracking, polar, and other optimizations on supply modulated PAs. And they all have this same block diagram. They just have different trajectories in this VN, V supply space. And this is from a paper by John Hoberstein out of University of Colorado Boulder. And the reference is all here. And this is the plot from his paper. And then additionally, John put a probability distribution function of a classic communication signal here. And you can see why having efficiency even in this regime is so important for this type of waveform, because you're down here at this lower range most of the time. And if you can have this high efficiency all the way through all of this regime here, it becomes a much more compelling architecture to utilize. Now, the technology that we use at Iridium is more of a direct polar transmitter architecture. Here it's a little bit closer to the EER trajectory that you saw in the previous plot. We use a constant envelope signal on the carrier path with just a phase modulator. So the phase of the pulses are moving back and forth to create the ultimate phase for the RF signal out here. And then we use a switch mode modulator here that's being driven by the envelope signal to clamp down on the signal and create the envelope around this from this phase signal that would be the RF path. And then we'll filter off the harmonics and other components in order to get the final RF signal out here. We've been able to achieve a 50-watt or 50% efficient board transmit path that has, this is the actual module. There's 3 gallium nitride chips here and then a custom IC here. Ultimately, we have a very high fidelity output signal Generally speaking, we could get twice the spectral density that one would normally get with a transmitter, and it consumes significantly lower power. And because it's so lightweight and dissipates so little energy, it winds up being a lot lighter, which makes it a lower cost unit to deploy. The idea is we're using an Open RAN architecture. So you'd put this 2 kilogram unit on a pole with a very short cable to the antenna, and then run a 5 gig fiber Ethernet cable back to the distribution unit, which then goes back to the centralized unit core, usually referred to as a CU and DU. And this, of course, is the radio unit, or RU. And so this becomes a very easy to deploy small cell. Here's some performance numbers of the module. And again, this is putting out an equivalent 5 watts and dissipating 20 watts total power. And again, it's very, very small, very, very lightweight. The efficiency of the GAN transmitter is running roughly 50%. With the other components on here, the overall power consumption or overall efficiency drops a bit because you have a lot of digital processing back here and conversion for the IQ signals into the various signal controls that are happening to get the high fidelity output. But ultimately, this is a lot less power for a small cell than other strategies. This is the entire module, which includes not only the board that you saw in the previous slide, but also additional power and processing units to do the lo-fi front haul interface and of course the DC power that's here. So in this case, this is where you have the Ethernet cable coming up, power supply coming up, and then RF going out. And ultimately RF coming back in to get converted back to a signal that goes down the Ethernet cable. This has a little bit more power consumed. It's 35 watts or 30 watts. And again, it's the same 5 watt peak output power that the card has. It's just that this includes everything you need to do a single small cell. This has this shows a typical analog linear amplifier, its constellation with a 256 QAM. This is what our PA performs with this full digital transceiver. And again, the final stage is roughly 50% efficient. But we've got EVM roughly 0.5%. And we can take it even further to 1024 QAM or even 16K QAM, which is much beyond even 6G as far as the 16384. Very high fidelity output, and again, very efficient in its creation of this signal. So again, the output power is in the order of 5 to 10 watt as far as a link budget equivalent, less than 35 watts of dissipated power. And this is actually our next generation product that we're looking at. This is 4 transmitters and 4 receivers. So that's a significant reduction in power compared to the last slide. The last slide was a 2x2, 2 transmits and 2 receives for 30 watts. Our current product under development is looking at eliminating quite a bit of that power dissipation. And we're looking at trying to operate it all the way from 600 megahertz up to the 4.5 gigahertz with just RF front-end card shifting to properly isolate the transmit from the receiver. So that's what we're looking at going forward. And so I'd like to conclude the talk to say that for efficient PAs, distortion will happen on your signals. So if that's going to happen, it's good to add in DPD to obtain the higher fidelity output that you really want, and at the same time achieve higher throughput. And to do that, you want to resize that final stage, either by dropping the supply voltage, which would increase the reliability, or if you've done it early enough in the design process and you can afford it, you can actually do a separate PA with a different size device. But often it's just dialing back the supply voltage will achieve a similar result. And then you want to reduce the wasted power. In order to do that, if you do a just-in-time delivery of the power to the RFPA with something like supply modulation, you can operate in that rail-to-rail scenario a larger percentage of the time and continually minimize that power dissipation of having a rail that's just too high for the overall waveform, or for the waveform at that moment. By designing these features into the transmitter up front, the system is able to provide a higher efficiency and throughput simultaneously and achieve those system-level performances. One of the techniques that I've shown in the talk is this doubly orthogonal matching pursuit. If you're going to pursue a digital signal processing strategy, looking at Juan Becerra's paper and being able to extract out the terms that are most impactful is a very good way to identify the most impactful terms and only include those that are most needed to give you the linearization that you need in your system. I do highly recommend closed loop inverse models. That way you can capture any changes that occur in the system as far as the compression characteristics changing over time. That creates a system that's much more robust. The inverse model can capture and compensate for other distortion terms, such as memory effects. I haven't gone through that specifically here in this talk, but I have done that in other publications. And finally, new dynamic supply architectures, such as direct polar, enable both high efficiency and high fidelity for small cell Open RAN RU systems. I want to thank you for your time and for your focus. I'm available to answer questions. If you'd like to discuss things further or get some answers to your questions, please email me at the email on the screen right now. And I look forward to that engagement. Thank you very much.
Okay, so it was a very interesting and informative presentation by Dr. Paul Draxler on envelope tracking as well as supply modulated amplifiers. So his presentation provided us with valuable insights. We appreciate the time and the effort Dr. Draxler invested in sharing his knowledge and expertise with us. So once again, thanks to Dr. Paul Draxler for his remarkable presentation. So now I would like to welcome Dr. Prasad Shastry sir onto the stage. Yes.
I just want to, Dr. Rosalind will not be there after 5 o'clock today. And we have a formal vote of thanks session after the last presentation, which we will do after coming back from the coffee break. But she may not be there at that time. So I would like to acknowledge all her efforts. And she has been a wonderful, a teammate, and she has taken care of a lot of things in the background. And I don't know, I don't have words to thank her enough. So thank you. Thank you. She has been, I know her since 2022 when I spent my sabbatical in RIT. and we have been working together, collaborating on many projects since then. And so I'm very happy that she is part of our SAGE, and her area of specialty is antennas, but currently she is working in the energy harvesting area. So thank you. Oh.
So now we have a coffee break for next 10 minutes. We'll have it, get refreshed, and come back immediately for the last session. Yeah.
Thank you. Hello again, everyone. It is my honor and pleasure to introduce to you the next speaker for the final technical talk of the symposium this afternoon, Mrs. Deb Dendy. She is a passionate engineer, executive coach, podcast co-host, workshop guide, wife, and mother. Currently, she is designated as the COO of McClin Connections, a company that focuses on leadership and relationship skills for culture transformation. She received her BSEE from the University of Wisconsin-Madison and MSEE from Arizona State University, focusing on millimeter wave IC designs. Ms. Dendy has been a visionary innovator and entrepreneur for over 35 years in the semiconductor industry, working for Motorola, US Monolithic, Viasat, and Anokiwave. Her engineering experience is centered around being an MMIC design engineer for satellites, automotive, and communication systems and applications. She holds 12 patents and has led teams ranging from 5 to over 100 people. Ms. Dendy held a variety of leadership roles, including Director of Engineering, VP of Operations, Senior VP of Human Resources, and Senior VP of New Product Introduction. She has challenged herself to transform and take on more impactful roles apart from technical duties to help personnel reach their potential and foster a more engaging and fun work environment for all. Ms. Dendy and her husband live in Arizona and have 3 adult children. Her hobbies include tennis, pickleball, kayaking, and lifelong learning, always looking to expand her skills for what's next. Some fun facts she would like for me to share with you is, there are 2 things. Dr. Prasad Shastry was her TA at the University of Wisconsin and fostered her love for millimeter wave design. And she wanted me to share this, that she, in her words, she hired an amazing and talented student, Scarlett Dawood, straight out of college, who quickly became an extremely important member of Viasat's millimeter wave IC design team, creating highly accurate component models and complex PA designs for satellite communications. So Ms. Dendy was actually my manager when I came out of college. So she will be presenting to us today a unique talk combining her engineering and leadership heritage with her current experience in synergetic teamwork coaching, titled The 4 C's to Design State-of-the-Art SoC. Please join me in welcoming Ms. Dendy.
Thank you so much. So let me share my screen here. And we will get started. Can you all see that okay? Yes. Wonderful. Thank you so much, Scarlett, and thank you, everyone. Good afternoon. I am really honored to be here today to speak with you all at this first SAGE International Symposium. I was thinking about changing the title of this talk to have to be Get C's to be really great engineer. But I realized for all of us in the room, who might have spent our whole scholastic career trying to get A's, that title might be a little too challenging. So as Scarlett mentioned, the title of my talk is going to be The 4 C's to Design State-of-the-Art SoCs. And I realize this talk may be a little bit out of place in a conference on advances in wireless technologies. But over the span of my 30-plus year career, making a lot of mistakes, I've learned a lot. I've learned that in order to work in teams that are truly innovative, creating new products and design methodologies that have never existed before, I really needed to learn skills beyond that of just engineering. So I've spent my career building teams, experimenting to see what works, figuring out what doesn't work, and working with great mentors and coaches along the way as well. So what I'm going to share with you today are 4 critical principles I learned that were not part of the engineering curriculum. And I call these principles the 4 C's. I discovered that I needed to master these principles in order to succeed and to live a good life. So what exactly are the 4 C's and why do they matter? So I'm going to give a brief overview of the distinctions and then we'll dive into each of them. So the first C is collaboration, which is working together to achieve a shared goal. Secondly, cooperation, which is working with others to help them achieve their individual goals. Communication, this might be one everybody recognizes, the sending and receiving of information. And finally, connection. A connection is the sense of closeness and belongingness a person can experience when having supportive relationships with those around them. So now I'm going to dive deeper into each of these distinctions, but first, let's talk about why these 4 C's matter. So in the early part of my career, I spent a lot of time in IC design, mostly gallium arsenide, gallium nitride technologies. And in those days, I was given a spec by the system engineer who had performed all the system simulations. So my job was really to turn that spec into a fully operational IC. And as far as the design went, the layout, EM analysis, even test, I worked largely on my own. If I ever got stuck, I could talk to my colleagues about it, see what they were doing. I presented design reviews to other colleagues just so there were some checkpoints along the way. And the 4 C's were important then too, but it seemed a little bit easier because the teams were just smaller. We had 1 to 2 engineers working on any one chip at a time. And because the mask sets were relatively cheap and there were only 11, maybe 15 layers or so, they were fast. It was easy to fabricate them too. They were very quick. So if the chip didn't work right, we could just iterate it, and it was pretty inexpensive. But I want to fast forward, and that's why I put up this slide today. First, I want to thank my good friend, Gaurav Menon, who's the Vice President of Engineering at Inauguration, for providing me this. I realize there's not a lot of detail on the IC side of it, but I don't think you'd be able to see it anyways because the layout is so compact. So this is one of the most complex millimeter wave 5G chips that has ever been introduced to the world. This was developed by Inauguration. The point I'm making with this chip, though, is to look at the left-hand side. So this was the product team. There were over 30 engineers and 20 unique roles on this single chip. And you can see, systems engineers, RF and millimeter wave, analog, digital. The list goes on and on of all the different disciplines that went into making this one chip. So this was a very complex chip and required for us to be working well as a team. The process itself had over 50 layers, and the mask sets for these type silicon processes cost in the millions of US dollars. The fabrication times with that number of mask sets are also very long. So you can imagine if there's a problem with the chip, this took 2 years to develop, and if there's a problem with the chip, it could take a year to reiterate and to get that back out to the customer. So all of these factors meant that if the team wasn't working well together, we were going to fail. And our customers wouldn't be happy. They might never buy anything from us again because they're counting on us to give them the next iteration of the design. Our bosses would be unhappy, and we might end up losing our jobs. We might not be able to take care of our families or work at the place that we wanted to, all because of this team and how we operated together. So this made learning how to collaborate, cooperate, communicate, and connect even more critical to our success. This is the largest team I've worked with on a single chip. And this really is the wave of the future. I have heard from other companies such as Broadcom and others that, and including Apple, that 30 engineers on a part is half or a third of the engineers that actually work on other parts. So it really makes learning these 4 C's and building teams even more critical as these chips get more and more advanced. So hopefully I've been able to iterate to you why this matters. So let's move on and talk about each of the C's. So the first C is collaboration, and this is working together to achieve a shared goal. So as we all know, innovation is a team sport. We work in teams, we build on each other's ideas, and this allows us to create something better than we could ever do on our own. Now, I was often told in school that you have to complete your work on your own, or in some cases, collaborating with others in school was considered even cheating. And so it's no wonder when all these students come out, and when I came out into the world of engineering, I had some difficulty learning how to collaborate with others because that was my background. That was what I had been taught. And I was really worried that, maybe if I gave out my ideas, maybe someone would take those or they'd take credit for them. Or, again, this was just the mindset I learned in school to do everything by myself. So this was really a big aha moment for me to realize that in order to succeed working with my teams in business, and in order to innovate at a very high level, I really needed to be open to sharing all of my ideas. And that's whether I thought they were really good or not. I had to set my ego aside and not worry if I personally got credit, but really giving my all for the good of the team. So my second point here is, how do you fully understand what the shared goal is? Early in my career, I would get assigned a small piece of a project, like I mentioned, a single mimic to design. And sometimes I didn't feel like I had time to fully understand the big picture, to look at all of the parts of the system that we would be working together and how my part fit into that. And because we were all busy with that schedule, you have to get the tape out done. Again, I thought there was not enough time to really learn all about the projects. And what I noticed is several times when my IC was being fabricated and then they integrated it into the next higher module, they had problems. They had problems because maybe the off-chip components I picked were too big, they didn't fit, they were too expensive. In another case, the biasing scheme I selected off-chip was too difficult to lay out on the circuit board. And these are perfect examples of I didn't fully understand the shared goal. So what did I learn from this? In order to make a great product, not just a mediocre product, we had to learn about the big picture. We had to learn how the entire system worked and how each of us contributed to and interacted with that system. And what that meant is that our IC team wasn't just the IC designers, the engineers. We started expanding that team to include mechanical engineers, the PCB designers, the test engineers, basically anybody who'd be contributing to the overall system, they were on the team. And what we found from that is we had so many great ideas together on how to improve the entire system because we now understood the shared goal. We understood what everybody was contributing, and we understood what the product was supposed to do, not just our part. We really created some extraordinary products once we expanded the team, and it was amazing. The funny thing was, I thought this was going to take too much time. To take the time to learn all about the system, I thought it was going to take too much time away, but what happened was, once we all understood the shared goal better, our designs actually took less time and we had less errors, which was amazing. You know, finally, the last point here on the slide, it's been shown time and time again that 2 or more people working together to innovate can beat a single person working alone each and every time. So I really learned to use that to my team's advantage. We engineers might have a little bit of a bad reputation of being introverted. I certainly know that I have identified myself as being introverted, and sometimes we prefer to keep to ourselves. I think this is a sign of brilliance, personally. I'm kidding. But I do think that we get a bad rap sometimes for being so introverted. And I have to admit, there have been some times where I just said, man, if I could just work by myself, I could really get things done quickly. But I learned that this doesn't work. When you're trying to build extraordinary products and really technological advances that no one has ever done before, you need to build that team. I also found that working alone wasn't as much fun as working on a team, because when others were truly collaborative, sharing with each other, teaching each other, it really made the environment much more fun, where people couldn't wait to come in to work every day because we knew we were going to create something wonderful. So that's collaboration. I'm going to move on now to cooperation. So cooperation is working with others to help them achieve their individual goals. So how do you find out what their goals are? This is an opportunity to take the time to speak with them. Speak with your teammates. Ask them questions about their personal goals, not just in your project, not just in their design, but in their careers, their lives. Who knows, maybe someone you know wants to be promoted to be a manager because they really care about people. How can you help them? Maybe they want to learn a new technology. How can you help them? You know, so many things in life can appear to be kind of a competition against each other rather than supporting each other. And I've seen this in business sometimes. I remember the feeling of having to compete for a promotion or a title with others. And it left me feeling a little bit isolated, because I had this thinking that was very short term, that in order for me to win a promotion, someone else had to lose. And again, I discovered that this was really short-term thinking, because I needed others to help me, just like everyone else needs help. But if I'm too busy competing and I'm not being collaborative and supportive of others, then they don't really want to help me. And it wasn't until I really noticed that, again, that aha moment, and started being collaborative and supportive of others early in my career, I really began to build strong networks of help. And all of these people around me were so vital to my career, and I was vital to their career and helping them. I also recognize that at times we all feel very busy. We just are busy doing the work we have, and that these conversations with our colleagues, again, take time. I used to think that this would take away the time I had for design, but I can assure you, when you're able to cooperate with your colleagues, you'll be surprised that you may actually feel less busy. You'll be more effective, more creative as a team, rather than just working harder. And finally, as part of cooperation, how do you demonstrate believing in others? So this is kind of an abstract concept. In the past, I thought believing in others sounded something like this. Oh, of course I believe in you. After all, you have the education, you have the skills to do the job, you've proven you can do it because worked on similar work in the past, of course I believe in you. But what I learned is that's really not believing in someone. That was me trusting them and recognizing they were competent, but it was me having a qualifier to believe in them. So now when I speak believing in someone, it sounds more like this: I believe in you. And you notice I didn't qualify it. I didn't add a reason. It's because fundamentally, I believe in people. Because what I've discovered is that all people really just want to do their best and contribute each and every day. And I've never met a person yet who woke up early in the morning to say, you know what, I'm really going to go out and be mediocre today, or I'm just going to try to get by today. No, people are amazing, and they really want to do their best. Now, you may be imagining a few people in your head that you're wondering, is that person really out there to do their best? I know I have a few struggles with some people as well, but don't let those people that are the outliers guide how you believe in others. Imagine your boss or a colleague or someone saying to you, I believe in you. What would that mean to you? What would that mean to your students? What would that mean to your colleagues for you to say that to them? What would you and your team be able to create if you chose to believe in each other and bring out the best each of you has to offer every day? It would be amazing. And I have personally seen it work in many companies that I have worked with. Believing in others really does lead to extraordinary results. And for all of you parents out there, this works really well for your kids too. When you believe in them, the confidence that they gain from it, they can set some of their fears aside and try things that they may never have tried without someone telling them they believe in them. So the next C is communication. Finally, she's getting to something that fits into this conference. So do you guys know how communication really works between people? This was another aha moment for me. So right now my vocal cords are creating sound waves, and those sound waves are propagating to your eardrum, vibrating the three tiny bones of your ear, and eventually sending an electrical signal to your brain. And that's where communication gets really interesting, because both of us who are communicating, I'm speaking, you are hearing, we don't have a fully correlated all-pass filter that allows us to understand exactly what the other person is saying, or especially what they mean. On the contrary, we each have our own filter, a filter of the way we were raised, our culture, the story our parents told us, what we learned in school, even what we learned from our friends and in our places of worship. Those are all part of our filter that shapes how we see the world, and it also shapes our perception of what other people are saying to us. So once that sound wave hits your ear and finally transmits to your brain, you use that internal filter to quite literally make up a story about what I said. So if I use the analogy of digital communication, if I'm transmitting ones and zeros from my brain, your brain performed its own translation of that signal that is not necessarily correlated to what I was saying. And you are trying to make meaning of what I transmitted. And the stories we make up about what others are saying isn't just limited to the spoken word. You know, have you ever received an email or a text where you just couldn't believe what someone was saying? You just couldn't believe the tone or the mood they were in. And then you followed up with them because maybe, you know, again, you were just couldn't understand why they were acting that way. But that was all the story that you made up about the words that you read. And so we are just story-making machines. And if you understand this fundamental of communication, then we can learn how to use that more effectively. So let's talk about some tools. The first tool I use is called Repeat After Me. And when you're listening to someone, rather than thinking in your head about what you think they're saying, just repeat every word they speak in your mind. Now, this has the benefit of keeping your mind from going off on tangents that draw your attention away and to help you stay engaged with the speaker, what they're trying to communicate. You see, people can speak about 150 words a minute. When I'm nervous, I can probably go higher, but our brains can process about 800 words a minute. So what that means is even if we are using this repeat after me tool, our brains are still wanting to add to the story. We're trying to add to the story of what someone else is speaking. So this repeat after me tool can be very challenging at times, just to be with the other person and really listen to what they're saying. And that leads me to the second tool. The second tool I call is being at nothing. So this is a practice where I try to set aside all my stories, my judgments of what the other person is saying, and I try to just listen and be at nothing. Now, this practice involves a lot of work, and you have to recenter so many times to try to put away your own voice that's speaking that story of meaning to yourself. You really have to learn to quiet those stories. As I was just mentioning before, now I just let others speaking pass over me, pass through me. And I don't try to judge it. I just try to listen. And I find this extremely important, especially when I've received that email or text that my stories that I'm creating emotion or I'm creating tone in that. It gives me a moment to stop and think with the person, to listen and listen without judgment, so that I can respond without being defensive. Because again, the mood, the things that the emotions I'm reading into a text, they're the story that I'm making up about it. And so this really helps me understand their message. And the other benefit is when I'm not thinking with my emotions, I can learn a lot more from others. I can be open-minded. I can really absorb what they are trying to speak. So finally, how do you as the listener verify what you interpreted that the speaker said and what they meant? And vice versa, how do they interpret what you speak and how you understand it? So it's really simple. It's always follow up and ask. If I say something after someone has spoken to me like, hey, the way I listened to you, I heard that you want me to do X, Y, and Z. Is that what you meant? And that gives the person speaking an opportunity to confirm their message, that that was indeed the message that they intended to transmit, or to explain if there was something that I missed. And that's often the case in communications between two people or more. There's some nuance that's missed. And if we all go our separate ways after that communication without those follow-up questions about, did you understand what I meant, or what did you hear from that? That really wastes a lot of time itself, because now we're not aligned with what we thought was said. And we're actually moving to our own stories of what we thought was said. So again, sharing your interpretations during the conversation helps avoid confusion, and it gives time to clarify in the moment. All of these tools that I'm sharing with you today have really helped me communicate more effectively. And if you really want to design and produce state-of-the-art SOCs with a team, these, like the ability to communicate is critical. So let's move on to the final C, and this stands for connection. So to remind you, connection is the sense of closeness and belongingness a person can experience when having supportive relationships with those around them. So this is the most overlooked and underused skill for teams who want to produce something extraordinary. So early in my career, I thought I needed to create this barrier between my personal life and my work life. I didn't share much about myself at work because, again, I'm a story-making machine. I made up a story that it was unprofessional to do that. Sorry about that. And I didn't connect with others, because when I wasn't willing to be vulnerable and to share about myself, neither were they. They didn't think it was a safe space if I wasn't able to share about myself. Sometimes I didn't speak up in meetings either because I was afraid. I was afraid others would judge my ideas as being stupid or that my ideas didn't matter. But what I discovered is when people are connected and can be vulnerable with each other, they can share whatever they are thinking without fear, without judgment, or fear of looking stupid or fear of making a mistake. So that being connected to others really creates a space where you and your team can build on each other's ideas because you feel comfortable sharing. And because you're connected to your team will listen. They'll be open-minded. They'll consider your ideas. You don't have to be afraid of how others are judging you and your ideas. And this is really as close to magic that can happen in innovation. Someone in the room starts with an idea, saying something like, okay, guys, I have no idea if this is going to work, but I think we should try X. And this inspires another person to add to the idea, something like, wait, what if we didn't just try X, but we also did Y? And the pattern continues. The team continues to expand on the ideas presented instead of closing them down or thinking that they're not valid. The team then begins to build on each other's ideas. And as I began to learn how to be more connected, I could be vulnerable about myself. I could be vulnerable with my team about things I was going through in my life, and they could be vulnerable with me and trust me. That started bringing out those ideas even more. People were not afraid anymore to share whatever was on their mind. Even when we disagreed, we could give our inputs and we could have a conversation instead of really invalidating others' ideas. We could have a rational conversation about what does that mean and how do we innovate from that. It made for an amazing, innovative team, but it also was a lot of fun. It was a lot of fun to be connected to other people, to know what was going on in their lives with their families. And it made showing up to work every day a lot more fun, a lot more enjoyable. I mentioned it before, but sometimes we engineers really get a bad reputation for being introverts, right? And we prefer to keep to ourselves. But this label of introvert, I know, doesn't help me connect with others. And if that sounds with you, there are a few experiments that I'm going to give you that you can try to connect with others. First, go out and talk to others on your team about their lives. Talk to them about their families, their interests. Take a genuine interest in the lives of others. Really care about them and share about your own life. Second, you can find ways that you can help others and also to allow them to contribute their help to you. A lot of times, yes, we love to help others. We'd love to volunteer to do different things. But when it comes to getting help ourselves, we hold ourselves back from allowing others to contribute to us. So finally, create the kind of team where it becomes second nature to ask for and to give help. If you develop these skills of connection and building trust, your teams will become more innovative, more trusting, more able to do things that are really extraordinary in the world. And I would say if your teams are struggling with this, find a coach. The world's best athletes, the world's best teams, they have a coach for a reason, because that coach can see things and help the teams really build on their skills. And finally, when I talk about team building, I'm not talking about firewalking or trust falls. Those things are entertainment, but they can be fun for a day, but there's no lasting results from that kind of team building. What it takes is really working together as a team on a shared problem, on communication, collaboration, cooperation, to really build that team so that they can learn to share anything with each other. Currently, I'm working at a company called Macklin Connection. We actually have workshops we run to teach people how to connect that are semester-long workshops. We've worked with so many different companies and so many teams that had kind of mediocre results. But after engaging with our company and engaging their teams in our workshops, they've transformed. They've transformed to be highly effective teams, really producing extraordinary accomplishments. So the other benefits we've seen with teams is increased capacity to innovate, increased capacity to create new ideas and products. We've also seen drastic increases in employee satisfaction, employee retention, company profitability, and get this, people are actually having more fun at work. So it's really, truly amazing what teams of people who are connected can produce in the world. So finally, I'm going to share one more. I'm going to talk a little bit about some of the stories of what I have learned before I learned how to build teams that were connected, that collaborate, that cooperate. These are all things that have happened to me in my career. I've worked in companies where the engineers didn't think they needed to build connections with others, like the operations people or the people who'd be fabricating the chip or even testing the chip. And I hate to say it, when I was working as an engineer early in my career, I thought that too. I thought that because my schooling was so difficult and I thought the design was really the most important part of the job, I thought that it was the engineers that must be the important role in the company and that the other people in the other jobs should really just listen to us. But the problem with that is that people don't work that way. Everyone wants to be on the team. Everyone wants to contribute, to be part of something bigger than themselves. And everyone wants to create something great. I've really witnessed this firsthand when the engineers chose not to get help from operations or the test team or even the fabrication team prior to completing the design. In some cases, I've seen parts go to fab that it took a year to develop and they were rejected by the foundry because the engineers had chosen to violate the design rules and the product just wasn't producible. So we had to do months of rework on this product. I've also seen products come back from the fab that couldn't be tested. The engineers hadn't spoken with the systems test team. So, some of the chips we worked on were so complex, so much going on in that chip, but they hadn't talked to the test team about how the chip would be tested, what equipment would be needed. And by the way, a customer will not buy a chip that can't be tested. So that turned out to be a pretty important thing to learn, is to, again, build the team, talk to the people who are going to be touching that part in any way. I have even seen something as simple as a lack of communication causing parts to not be able to be shipped because we didn't have the appropriate size tape and reel. We didn't have the appropriate packaging to actually ship the product when it came back from fab. So again, all of these things happen because there's a lack of communication, a lack of collaboration. All of these sees how important they are to build up, to build up so that you don't have to learn some of these failures that I have made in my career and others have made as well. Again, finally, what I learned from all of these is just to really expand what your idea is of who is on the team. So my team isn't just engineering, it's not just operations. My team is everybody working together to produce something great. By the way, that also means your vendors are on your team, your customers on your team, and the more I could create opportunities for everyone on the team to share and contribute, the result was nothing short of extraordinary. We were able to produce the first ever 5G millimeter wave SoCs, and we delivered those in millions of quantities. And that we were a company of 100 people. And our ability to be able to do that was all based on the teamwork, the collaboration that we did as a highly functional team. So I'm going to share a bonus C with you today. So the bonus C is care. And that's really the foundational element of all the other C's. It's the foundational element of building an extraordinary team of people who can collaborate, communicate, connect, and cooperate. So the fact that you and your team care for each other as people is really essential to building great teams. But sometimes in our everyday lives, we can get busy and we can often take this essential element for granted. So if you're interested to learn more, if you have questions, please feel free to reach out to me. My email is there on the slide, deb@macklinconnection.com, to learn more. Again, we teach workshops designed to help teams be able to produce extraordinary accomplishments, and so critical in our field of engineering for people to be able to innovate and build those strong teams. I also really want to thank Prasad and Scarlett for believing in me and for giving me the opportunity to speak with you today. I'm really excited to be especially invited to speak at this inaugural event for SAGE, and I just thank you so very much. And so finally, I'm going to invite you to be curious at this point. Do you have any questions? Was there a part of my presentation that really got you thinking, or maybe it perturbed you in some way? What showed up different for you that you can use with your team? Or maybe someone courageous could even share something they've learned from their past mistakes with their team. So I open it up to all of you. Do any of you have anything you'd like to share?
Yeah, thank you. Hi, Deb. This is Girija, and I totally agree how important the 4 C's are to work as a team. I've worked in software, I've managed global teams, and with virtual teams all over, this is so important to focus on the 4 C's. And especially here in India, when we have engineers from different states, and they're so comfortable communicating in their own languages. But then as a team, it's so important to communicate in English, especially at work. I've had a lot of such experiences where I've, encouraged teams to, how to kind of engage in the right communication, be it with within the team or with the clients or customers. So I totally agree with what you've. It was a fantastic session, which is, I think, very important for teams to be successful in delivering any product. So I didn't have any question. I just wanted to share this.
Well, thank you so much. Yeah, you brought out even another distinction of those filters that we all have, right? Those filters and how we're making up stories about what others are saying. Well, if we don't speak someone else's language, I don't know if that would be no filter at all. Like, we can't understand, right? We literally don't have any story to make up because we don't understand. And what a great observation to think about. Yeah, even when if we're all speaking different languages, we can't connect with each other because we're not in a place where we're able to.
Yeah, Miss Deb Dundee, it was very well explained the role of 4Cs in our technical journey, which lead us towards the progress and success. So your presentation has added our concluding remarks and vote of thanks. I would like to invite our esteemed executive board members onto the stage to share their reflections on today's sessions and extend their gratitude to everyone who made this event possible and successful. So please join me in welcoming the executive board members as they deliver the concluding remarks and vote of thanks. Yeah.
Have after this concluding session, the interactive session, a high tea networking and student industry interactive session. Those are going to be there. So I think you'll have made an announcement on that? Or? No, not. You are going to make it separately. Okay. So, so I also invite our executive board members to say a few things in conclusion, in some remarks, if they have any. But to me, I think it was a very good, successful inaugural session and the symposium too. So I really appreciate all of you taking your time and making an effort to be here today. It means a lot to the organizers of this symposium. And also I want your feedback on what happened today and how to improve it in the future. If we were to do this again, what changes could we make? How can we do it better? That's the whole idea here. So feel free to talk to any of the volunteers, any of the organizing committee members, and give your feedback. So having said that, are there any other comments? There is also vote of thanks. I want to call people to thank. Do you have anything to say, Dr. Corey? Yeah. And also Aparna? Yeah, please do come. Okay. Yeah, please come. And also Dr. Nayak.
First of all, thanks to all of you for staying till the end of the session. Thanks to all of you. Just a couple of points. One is that as a SAGE, we have explained what we plan to do, but we are most open to any ideas in which we would like to do. We are open to do these programs, that it could be training, consultancy, whatever aspect of it. We have large number of experts, so just don't go by one or two people who spoke here. I may not be as knowledgeable, but I am sure that our team has a large number of experts available, so we will be happy to help you in any part of the training. It could be that we could organize such seminars in the areas in which you have interest, that we could do, or we could customize certain things which are needed for your organization or institution, and we could do both online, offline, at some such central place where we are doing, or we could come to your organization and customize and do those programs. So we are open to all possibilities. I would like on behalf of SAGE, extend this and then request all of you, our emails and other details are available. Please feel free to contact us, and then we could try to organize those events as you need it. And also, as Professor Shastry mentioned, that probably after a few remarks from our team, some of you could also come and give your feedback here so that we really get online real-time information, what is your feeling about this seminar and what are your requirements. And then also you can send it through email. Thank you.
Is Scarlett still there on Zoom? Can you check, please?
Yes, I'm still here.
Yeah. Yeah?
Yes, I'm
You there?
still,
Okay.
yeah, I'm still here.
Yeah, can you, there she is, yeah.
Yeah, hello. I think this was such a successful event today. It was an honor to have all of you here with us for this first symposium and inauguration. And I totally agree with Dr. Corey, about customizing and receiving feedback so that we have an idea how to build. We can customize different types of workshops, seminars, training. We had mentioned, like Dr. Corey said at the beginning, what we are planning to do with SAGE, but we would love to have feedback, especially that we have a mix of both academic and industry here with us today. So thank you, everyone. I also want to say thank you to everyone who was on the field out there working. I wish I was able to be with you all today, but one day I will be there. So thank you for everyone who put this event together. There was so much work in the background that happened to make this day possible. And I also want to thank all of the speakers who came, the guest speakers during the inauguration, during the symposium. Thank you so much for taking all of the time to prepare in the last few months with us and to make this possible for us today too, to listen to these wonderful talks that were given today. And also special thanks to the technical team for making this possible so that we can be able to have this as a global international event, and that I will be able to also be part of it, and so many others can be a part of it too from across the globe. So thank you so much.
I just want to say Scarlett has worked very hard. I mean, she is a hard worker on anything she focuses on. But this symposium, she worked very hard. In the last few days on getting the live streaming going on YouTube, she really worked hard and solved all the problems. Thank you, Scarlett, for all your hard work. Thank you.
You're welcome. Thank you.
So now I invite Aparna to...
I would like to thank each and every one of you for staying with us till the end of the symposium. And I think Dr. Shastry will give a detailed vote of thanks, but a special shout out to the technical crew, the event factory event planners, and all the people who have worked behind the scenes, like Dr. Roslyn, Dr. Parimla, and all the student volunteers. You were really good today. And without all of your help, we couldn't have achieved what we wanted to achieve today. Thank you so much, and we'll see you shortly in another symposium. Thanks.
Good evening, namaskara. First of all, I would like to thank Professor Prasad, S. N. Prasad, to give us an opportunity to speak to you today, and for formulating this SAGE. Somehow I felt that this is the need of the hour, and I feel, that's my personal feeling is today I think we have only what you call, we have put the seed on the ground, okay? The sage has to grow and, flourish. And for that, a lot of, you have to do watering, tinkering, all things needs to be done. It's like a gardening, right? So that means you have to have, all the people have to come together. It is not one man, Professor Prasad, myself, or Corey, or all other executive members, or the volunteers and all things. I feel this should be a movement sort of thing. We are trying to bring in academia and the industry, and basically all RF people. This is not only we are thinking of doing as a training or sort of a thing. It is not there. So I want all of RF people coming together to make this community sustain and for a longer period and grow. That is the intention of SAGE. Basically, I thought it is not only some training and we'll do. That's basic things. But the larger image or the vision is that how to bring the RF community together and doing good for the humankind. That should be our game. Okay. For that, I think everybody has to contribute. It is not we SAGE as an industry or the people who are here and not here also. In that sense, I want everybody of you to be the ambassadors of SAGE should be there today. That is the things what I'm trying to tell. It is not that, this is not the SAGE community. I want SAGE community should not be even be able to accommodate in any one of the biggest halls. That should be the things. Okay. I'm not saying the Modi auditorium, 1 lakh people can stay. I said the SAGE community should be bigger than that. To do that, everybody has to contribute. Okay, so this is today is the first day. I'm saying we are only what you call bow seeding karte hai na, wo Kannada mein neer aakti wala. So in that sense, this is the T0 today, right? We have got T0, T1, T2, T3, 300, right? So from that angle, please take this message backwards. You bring whoever is the RF guy, if you know across, please try to inform to us, okay, who is interested in RF or work for the RF right now or the future likely to be there. That's what I'm saying. Students, is your responsibility. Make this team grow. I'm finding it is reducing. That should not be. The reverse has to happen. Okay. So you have to tell your college mates, whatever who are there, all the faculty is there. They have to tell the students that it is more flourishing, more interesting, it likely to be there. That positive feedback you have to take. And that has to go that's more important for this today's meeting. Thank you.
Thank you, Dr. Nayak. This also, I would like to thank all the speakers today, starting from the chief guest, guest of honor, and all the symposium speakers. They made a sincere effort to participate in this. So we learned a lot from all of them. So thank you very much. I appreciate it. So the symposium organizing committee, apart from the executive board members, they have consisted of the following. Dr. Parimala Prabhakar, she has been helping us and working very hard for a long time. Thank you very much.
Thank
you. On behalf of SAGE. So you are part of SAGE, but still we have to thank you on behalf of SAGE.
All with your guidance. Thank
you. Similarly, Professor Nisha, is she here? Oh, there she is. Yeah. She has been, while Dr. Parimala Prabhakar took care of coordinating the program as a program coordinator, Professor Nisha helped in 2 areas. One is in the cultural program committee and also in the volunteers, student volunteers committee. So I would like to give this as a token of our appreciation. And then we have Dr. Rosalind, who also was felicitated. She could not stay longer, so she has already left. She also helped us a lot, and our thanks for, for all that help. Then we have Dr. Bhupalan. Is Dr. Bhupalan here? Yeah. But Dr. Parimala Prabhakar, as well as Dr. Nisha and Dr. Rosalind are from RIT, Ramaya Institute of Technology. They are professors there, whereas Dr. Bhupalan is a professor from VIT Vellore, Vellore Institute of Technology. He has been part of SAGE, and he has been helping us a lot. Dr. Bhupal is so enthusiastic, during this trip of mine, he already said that, he has some ideas about doing some workshops jointly with SAGE. So we will talk about that. Thank you. Then we have Dr. Nutan Venkatesh. Dr. Nutan Venkatesh is also a professor in Ramaya Institute of Technology, very enthusiastic and active member. So he took care of all the student volunteers and making the certificates. And he was also in the audiovisual committee. He gave a lot of suggestions and took care of a lot of things. Thank you very much.
No problem.
Thank you.
Few things. My input to the SAGE group, I think the present generation need RF people means they want to have a training from industry. So they have a concept of internships. So if SAGE group has an opportunity to connect with the industry people, certainly the students will come up with new ideas to give suggestions to the industry with their skill sets, and industry will exploit or harvest their energy in giving back to the society. I think there the gap can be filled. That is what my suggestion is. Please, I think Tejas networks of people were talking. I think many of our students are there. So if they get an opportunity to work with the industry, certainly I can see my students are more enthusiastic in giving out their energy to the free space, which is more powerful now.
Okay, thank you. Thank you for that suggestion. In fact, this idea of student-industry interaction came about little late in our planning of this conference. So even then, with the available time, with the help of Dr. K.D. Nayak, we were able to get support from 4 people from industry as moderators to conduct that interactive session. So that's going to happen in the next hour. So I think that is something unique. If that is in demand in future, we would encourage more students to participate, and the people from industry are always available. But it's the students who have to take interest and come forward. So that is a unique thing. We should continue that. And also I'm thinking that we should have a panel session with some industry experts and some academicians and discuss on an important topic, current topic, which is of interest to the whole country in different technology areas. That's very important. I have seen that in our ISM we used to do that. I have participated how to recruit or how to make students get interested in RF area, etc. I have participated. So we should have whatever is appropriate at that time, we should have those topics. So we will do that. I think that's a good suggestion. Then we have Mr. Premnath from RIT, who also helped us in audio-visual. So Mr. Premnath is in charge of the labs in the CARVS, that is Center for Antennas and RF Systems in RIT. Then we have, we already thanked our invocators in the morning. And then all the flower arrangements that you see here was provided by Fluorescence, which is a florist business by Kalpana Swami. And please, she is here in the audience, so. Fluorescence. Thank you very much. Thank you.
Wait one.
It's okay. Then we also have, I also want to recognize our event planners from Event Factory, and some representatives are here, Smiti Kapoor and Preeti Kamatar. Oh yeah, Deepak and also Tabriz. Yeah, all the four. Do you have? Thank you very much. Huh? Oh, sorry. Okay. Huh? Yeah, yeah. Very sorry. Oh, okay. Thank you. Thank you very much. And of course, this particular venue, the manager, Mr. Zamir and his team, also I want to recognize. They are not here in the room right now, but they did an excellent job. They were very accommodative, very flexible. After I came here, I have come here at least about 6 or 7 times in person for various things, and they were very cooperative. And even today, you can see the outstanding arrangements, the food, and everything. And so we wholeheartedly thank them a lot. And the venue, I hope all of you enjoyed the venue. Venue is fantastic, venue. So, yeah, and the food too. Yeah. The Prestige Falcon Tower, yeah. Then we have all the volunteers here, the student volunteers. So I would like to recognize them. And we have something? Yeah, they have all been given certificates already, and also they have been given some conference goodies. There are bags outside they are going to pick up, right? So. Okay, I'll let you. Okay, you please pick up at the registration desk. So there are bags there, and probably they will put it in the bags. Yeah, yeah. Okay. So have I missed anybody? Do you think? No, I should also thank our executive board and our advisory board. Professor Surendra Pal, then we have Dr. K.D. Nayak, Dr. Corey, Aparna here, and the Scarlett virtually. Okay, thank you. No, I could not have done it without all your support, ideas, and encouragement, cooperation, and hard work. Thank you very much. Yeah, in fact, you used the word family. In fact, we work like a family all these years, and we will continue to work like that family. Thank you very much. No, my bouquet is there. I think. Yeah.
Since you acknowledged me. Well, thank you for acknowledging me, Dr. Corey, and all of you. What I want to say is, I cannot tell you in my heart how happy I am to see this day, because when we first thought of this idea, it just seemed so impossible. It was during COVID, and we were all bored, as you all remember how bad COVID was. And that was the time when this idea came to his mind. I had no idea that on this day we'll be sitting here with this first inaugural event taking place with so many of you helping my husband to achieve this. And as you said, it is just the first step. And we want all your cooperation in the future as well, because as he said, I have always been astonished how few RF engineers. You're such a small community among all the other engineers, and I don't know why it is. I've been told various reasons, but there is so much potential. Everybody is holding in your hand this thing in your hand. All of you, raise it. You could not have this thing without all these guys, okay? That is the point. You cannot have a wireless phone without a wireless engineer. You cannot have aeroplanes flying in the sky without having a wireless engineer like Aparna. So you have to think about this, and please, as you said, go to your own communities and let people know. This may be hard stuff. I don't understand it. I'm not an engineer. But there is absolutely no reason why India cannot achieve whatever it wants to achieve. And our current government is trying to help. And we just need to have more people come forward and reach out to other people, friends, family, whoever, and let them know that we have this group of experts. We saw this lady getting up in the middle of the night, in the early morning, so many thousand miles away just to be a part of this. So I'm really, really appreciate all of you, but please remember you have to keep this going. Thank you. Then I have to give it back to you because I'm not taking it to anyone.
On behalf of all of us, we would like to honor Prasad Shashi sir and Madam Sunita Prasad ma'am.
So this comes to a conclusion of this concluding session. Just want to make one point. I didn't say this in the morning, but I have often said this, that I have served that country for 42 years now, United States of America. And I strongly feel that it is time for me to give back to this country which educated me and made me who I am today, and went to that country. So that's my feeling, my inner feeling. So I chose this route rather than designing a circuit, getting a patent and manufacturing it and selling it. That's how the many startups do. Instead of that, we chose this because we saw a need, and also it falls in line of all our what we do, what I do, and what I have been trained all these years. So that's, everything came together, and that's the reason we began. Thank you.
Thank you, sir. So now we have high tea and a networking time. So immediately after that, we are the most anticipated segment of the today, that is student industry interaction, will be held in Merlin Conference Room. So that is adjacent to this conference hall. Yeah. Yes, sir. Yes, sir. I'll give the mic. It's there.
Well, first of all, thank you, Professor Shastry, for inviting and arranging such a thing. I want to make two comments. You see, we RF engineers, Dr. Corey already told, we have started a group also we called Microwave Tigers. And we don't have many members in that one. There are 4,300 tigers in the country, and we have got less than 1,000 microwave engineers in the country. So that is the situation. The fact is like that only. Of course, I did not include the students. We RF engineers have got one problem, which Dr. Nayak will not agree. We have got an impedance mismatch everywhere. And Professor Shastry tried to match this one. See, academia, industry, and R&D, I find that there is matching in that one. I hope your effort will bring them together. And yes, he is a matchmaker. So impedance matching is essential for it. And why industry and academia and R&D, they don't work together? Since I had been in almost all the aspects, like in the academia also, in the industry, associated with industry, and of course R&D. Mostly we think that academicians can write the papers and they don't know what paper tigers. Academia, I told you. Industry, no, we have to deliver. Somehow we have to make it work. And R&D persons say we are the best. So in that way, and this effort should bridge this gap in between. There should be impedance matching. And I definitely thank Professor Shastry, Dr. Corey, Dr. Nayak, and others for this effort, and thanks for bringing me here. I had been microengineer for almost almost 54 years. I find this is essential for the country's progress. Thank you.
I'll just make a few comments. I have known Dr. Prasad since my early days at Northrop Grumman in probably 35 years ago, So we started interaction. We used to talk a lot about, there are so many RF people in the US, and there was a big community, and it grew rapidly. And I said, how come India has not done some amazing things in RF? And over the years, things changed. And I'm really glad to see that this whole seminar and what the talks they gave here today is an example of what advanced things are going. And even some of the talks I heard in the last few years at the conferences. So it's really great to see India has progressed a lot. I and Dr. Prasad used to discuss, India could be a very strong leader in semiconductors and RF because in the US there are so many people, including me, who have worked for so many years in the US. So it's good to see many people coming back. I came back to India and started a company in RF. Dr. Prasad has spent so much time in this whole community. organizing this SAGE talk. So it's been really great to see, advancement in RF because of everybody's efforts. So today's program was definitely an example of what we can do, and more things like that probably needs to happen. Dr. Prasad and I used to discuss, this is many years ago, that why India, in today's phones, the percentage of chips made in India, what is it? It's probably close to chips made in India that are used in the phones today is probably close to less than 1%. And that all can change if all of us decide that, there is a very good platform like Make in India and all these things, and the government is taking steps in the right direction. So all these things will hopefully change, but to compete in the world, to really, have lots of chips manufactured here, is still a big goal that is really, it can be achieved, but everybody has to work hard. So this is a step in the right direction. So I want to thank Dr. Prasad and the SAGE community and what they have achieved. It's a good step in the right direction. And really, congratulations to everybody who's participated in this. It's really been a very, very nice conference. Thank you.
Thank you. On behalf of SAGE, we really appreciate your cooperation and support. So we really appreciate your unwavering support and guidance.
Thank you, everyone. So now let us make a move to the Falcon cafeteria. So I request, sir. Okay. So now the place has to be given to the next session, that is a mesmerizing string event, puppet show. So we will all take our things and make a move to the Falcon cafeteria, followed by the industry student interaction at Merlin conference room, that is just adjacent to the conference here, right? So we will lead you there. So students, stay back with us, and also the industry people who has come for the delivery of their perspectives. So we'll take it forward. Thank you.
In the Falcon Cafe, there is high tea provided, and then the interactive session is in this foyer. There is a room. That's where it is. Thank you.